Good evening, dear listeners. As you settle in for the night, prepare to embark on an extraordinary voyage, a journey that will take us 27,000 light-years from Earth, through veils of cosmic dust and glowing nebulae, to the very heart of our Milky Way galaxy. Tonight, we're going to explore one of the most profound discoveries in modern astronomy, the true size of Sagittarius A*, the supermassive black hole that anchors our galaxy. This is a story of cosmic extremes of objects so massive they warp the fabric of space and time itself, of temperatures that exceed the cores of stars, of gravity so intense that not even light can escape. But it's also a human story, of decades of patient observation, of brilliant minds working together across continents, and of our species' unending quest to understand the universe we inhabit. Before we begin this cosmic adventure, I invite you to like this video and subscribe to the channel. Your support gives me the motivation to continue bringing you these deep explorations of our magnificent universe. And now, let's drift into the dream of exploring the vast cosmos together with AstroMind. So relax, breathe deeply, and let your mind wander to the farthest reaches of space. The monster at the center, in the depths of space, 27,000 light-years from Earth. Hidden behind veils of cosmic dust and glowing gas, lurks a monster. Not the kind from science fiction, but something far more real and infinitely more extraordinary. At the very center of our Milky Way galaxy, in the direction of the constellation Sagittarius, resides a supermassive black hole, a cosmic behemoth so massive that it contains the equivalent of 4.3 million suns, compressed into a region smaller than the orbit of Mercury. For decades, this object existed only as a mysterious radio source, a bright spot in our telescopes that hinted at something profound, yet remained frustratingly enigmatic. Scientists called it Sagittarius A*, with the asterisk denoting its exciting nature, a designation chosen because in atomic physics, asterisks mark atoms in excited states, and exciting it certainly is. This is not just any black hole. This is our black hole, the gravitational anchor around which hundreds of billions of stars, including our own sun, perform their cosmic dance. But here's the fascinating part. Despite its immense mass, despite being studied for nearly 5 decades, we've only recently been able to answer one of the most fundamental questions about this object. Exactly how big is it? The answer came in May of 2022, when an international team of over 300 astronomers unveiled the first direct image of Sagittarius A*. What they revealed changed everything we thought we knew about the heart of our galaxy. Tonight, we're going to journey to the center of the Milky Way. We'll explore how scientists finally measured the true size of Sagittarius A*, discover why this measurement was so extraordinarily difficult to obtain, and understand what this breakthrough reveals about the nature of black holes, gravity, and the very fabric of space and time itself. So settle in, relax, and prepare to voyage to one of the most extreme environments in the known universe. Chapter 1: The Discovery of the Galactic Center. Our story begins not in the modern era of supercomputers and space telescopes, but in the 1932, during the Great Depression, when a young engineer named Carl Jansky was trying to solve a much more practical problem. Jansky worked for Bell Telephone Laboratories in New Jersey, and his task was to investigate the sources of static that interfered with radio communications, particularly the transatlantic radio telephone service that was becoming increasingly important for global communication. To accomplish this, Jansky built a unique antenna system, a contraption mounted on wheels that could be rotated to determine the direction of incoming radio signals. Day after day, month after month, Jansky meticulously recorded the radio signals his antenna detected. He identified several sources of static, nearby thunderstorms, distant thunderstorms, and then something else entirely. A persistent hiss that seemed to come from beyond Earth's atmosphere. At first, Jansky thought this mysterious signal might be coming from the Sunday, but as he continued his observations, he noticed something peculiar. The signal didn't follow the sun's daily path across the sky. Instead, it moved slightly each day, rising about 4 minutes earlier. This 4-minute difference is the signature of something following sidereal time, the time it takes for the Earth to complete one rotation relative to the distant stars, rather than the Sunday. Whatever was producing this radio signal was coming from far beyond our solar system. Through careful analysis, Jansky determined that the radio waves were emanating from the direction of the constellation Sagittarius, toward the center of our galaxy. In April of 1933, when he announced his discovery, Jansky had no idea he had just opened a window into an entirely new realm of astronomy. The implications were staggering. Space was not silent at radio frequencies. The universe was broadcasting, and we had just started listening. Jansky's discovery represented the birth of radio astronomy, a field that would revolutionize our understanding of the cosmos. But the full significance of what he had detected wouldn't become clear for decades. The radio source that would eventually become known as Sagittarius A lay hidden within the broader radio emission Jansky had discovered, waiting for more sophisticated instruments to reveal its true nature. The next major breakthrough came in the 1950 seconds, when Australian astronomers Jack Piddington and Harry Minnitt, using radio telescopes in Sydney, detected a discrete and bright radio source in the Sagittarius-Scorpius region. Their observations, made with increasingly powerful radio telescopes, confirmed that there was indeed something extraordinary at the center of our galaxy. But the technology of the era still couldn't resolve the fine details needed to understand what was producing these radio emissions. It wasn't until February 13 and 15, 1974, that astronomers Bruce Ballack and Robert Brown, using the baseline interferometer of the National Radio Astronomy Observatory, discovered a compact, bright component within the larger Sagittarius A radio source. This compact source was unlike anything they had seen before. It was incredibly small, incredibly bright, and clearly represented something of profound importance. They designated it Sagittarius A*, and that asterisk would prove prophetic. The existence of Sagittarius A times raised immediate questions. What could produce such intense radio emissions from such a small region? The object was clearly compact, far smaller than a typical star cluster or nebula, yet it was producing enormous amounts of energy. The answer, scientists would gradually come to realize, lay in one of the most exotic predictions of Einstein's general theory of relativity: black holes. Chapter 2. The Hunt for the Black Hole. The concept of black holes has a long and fascinating history that stretches back even before Einstein. In 1783, the English natural philosopher John Michell proposed the existence of dark stars, objects so massive and compact that not even light could escape their gravitational pull. He based this idea on Newton's corpuscular theory of light, which treated light as particles that could be affected by gravity. Michell's dark stars were a theoretical curiosity, an interesting thought experiment, that seemed to have little connection to the real universe. Over a century later, in 1915, Albert Einstein published his general theory of relativity, which fundamentally changed our understanding of gravity. Einstein showed that gravity was not a force in the traditional sense, but rather a consequence of massive objects warping the fabric of space and time itself. Imagine space-time as a stretched rubber sheet. Place a heavy ball on the sheet, and it creates a depression. The more massive the object, the deeper the depression. Objects moving near this depression will have their paths curved by the warped space-time. This curvature is what we experience as gravity. Just months after Einstein published his equations, the German physicist Karl Schwarzschild, while serving on the Russian front during World War I, found an exact solution to Einstein's field equations. This solution described the space-time geometry around a spherically symmetric mass. What Schwarzschild discovered was remarkable. His solution predicted that if enough mass were compressed into a small enough volume, it would create a region of space-time so severely warped that nothing, not even light, could escape from within a certain radius. This boundary became known as the event horizon, and the object it described would eventually be called a black hole. For decades, black holes remained purely theoretical. Many physicists, including Einstein himself, doubted that such extreme objects could actually exist in nature. They seemed too bizarre, too contrary to physical intuition. Surely, they reasoned, some physical process would prevent matter from collapsing to such extreme densities. The universe couldn't possibly allow something so strange. But the universe, as it often does, proved far more imaginative than human intuition. In the 1960 seconds, theoretical work by physicists including John Wheeler, Roger Penrose, and Stephen Hawking demonstrated that black holes were not just possible, but inevitable consequences of general relativity. Massive stars, when they exhausted their nuclear fuel, would collapse under their own gravity. If the star was massive enough, nothing could stop this collapse. The star would compress beyond its event horizon and form a black hole. These stellar mass black holes would typically contain a few to a few dozen times the mass of our Sunday. But Sagittarius A times was something different entirely. As astronomers studied the motions of stars near the galactic center throughout the 1990 seconds and early 2000s, they realized they were dealing with a black hole on an entirely different scale. A supermassive black hole containing millions of solar masses. This raised new questions. How do supermassive black holes form? How long have they existed? And crucially, how can we prove that Sagittarius A times really is a black hole? The key to answering these questions lay in careful observation of the stars orbiting near Sagittarius A*. Two teams of astronomers, one led by Reinhard Genzel in Germany and another led by Andrea Ghez in the United States, embarked on multi-decade campaigns to track individual stars as they orbited the invisible massive object at the galactic center. This work required extraordinary patience and technical precision. The stars are incredibly distant, the region is shrouded in dust, and the movements are rapid. Some stars complete their orbits in just a few years or decades. Using advanced infrared telescopes that could peer through the obscuring dust, these teams tracked stars with designations like S2, S4, and S14 as they whipped around Sagittarius A times at speeds reaching thousands of kilometers per second. One star, S2, became particularly famous. This star follows an elliptical orbit that brings it extremely close to Sagittarius A times every 16 years. In 2018, as S2 approached its closest point, it was traveling at approximately 25,000 kilometers per second, about 2.5% of the speed of light. By applying Kepler's laws of orbital motion to these stellar trajectories, the teams could calculate the mass of the object the stars were orbiting. Both teams arrived at similar conclusions. The invisible object at the center contained approximately 4 million solar masses. Moreover, this enormous mass had to be contained within a relatively tiny volume. If you tried to pack 4 million suns into a region the size of our solar system, you couldn't do it. There simply wouldn't be room for that many normal stars. The only object that could possess such extreme density was a black hole. The observations of S2's close approach in 2018 provided another crucial test. Einstein's general relativity predicts that light climbing out of a strong gravitational field will lose energy and shift toward longer, redder wavelengths, a phenomenon called gravitational redshift. As S2 swung past Sagittarius A*, astronomers detected exactly this redshift, precisely as general relativity predicted. This was smoking gun evidence that Sagittarius A times was indeed a supermassive black hole. For this groundbreaking work, Reinhard Genzel and Andrea Ghez were awarded the 2020 Nobel Prize in Physics, sharing the honor with Roger Penrose, who was recognized for his theoretical work, showing that black hole formation is a robust prediction of general relativity. The discovery that Sagittarius A times is a supermassive compact object was now confirmed beyond reasonable doubt. But one fundamental question remained: what does a black hole actually look like? And more specifically, how big is it? Chapter 3: The Challenge of Imaging the Invisible. Here's the paradox that makes imaging a black hole so challenging. By definition, a black hole is black. The event horizon marks the boundary beyond which nothing can escape, not matter, not radiation, not even light. This means that the black hole itself is, quite literally, invisible. You cannot see it directly any more than you can see the darkness of a shadow. So how do you image something that by its very nature cannot be imaged? The answer lies in what surrounds the black hole, rather than the black hole itself. While nothing can escape from within the event horizon, the region just outside the event horizon is anything but empty or quiet. Material falling toward a black hole doesn't plunge straight in. Due to conservation of angular momentum, infalling matter spirals inward, forming a swirling disk called an accretion disk. This is where things get extraordinarily interesting and extraordinarily hot. As gas and dust spiral inward through the accretion disk, they experience intense friction and compression. The particles rub against each other, collide, and generate heat, enormous amounts of heat. The closer the material gets to the black hole, the faster it moves and the hotter it becomes. In the innermost regions of the accretion disk around a supermassive black hole, temperatures can reach millions or even billions of degrees. At such temperatures, the matter doesn't just glow. It blazes with radiation across the entire electromagnetic spectrum, from radio waves through visible light to X-rays and beyond. But even this glowing accretion disk isn't what astronomers hope to image. The real prize was something more subtle and more profound: the black hole's shadow. To understand what a black hole shadow is, we need to think about how light behaves near a black hole. Einstein's general relativity tells us that massive objects warp space-time, and light must follow the curves of this warped space-time. Near a black hole, space-time is so severely curved that light rays are bent into dramatically curved paths. Imagine light from the accretion disk trying to reach your telescope. Some of this light travels relatively far from the black hole and reaches you with only slight bending. But light that passes very close to the event horizon gets bent so severely that it curves around the black hole, sometimes orbiting it multiple times before either escaping to reach you or falling past the event horizon. This creates a complex pattern of light and shadow. The shadow itself is approximately twice the size of the actual event horizon. This happens because there's a critical radius around the black hole where light can orbit in an unstable circular path. Any light emitted closer to the black hole than this radius will inevitably fall in. This creates a dark region, the shadow silhouetted against the glowing backdrop of the accretion disk. Imaging this shadow would be the ultimate confirmation that we're seeing the signature of an event horizon, the defining feature of a black hole. The challenge is that black holes, even supermassive ones, are incredibly small when viewed from Earth. Sagittarius A times has an event horizon diameter of about 44 million kilometers, roughly the distance between the Sun and Mercury. Sounds large, right? But remember, this object is 27,000 light-years away. 1 light-year is about 9.5 trillion kilometers. So we're trying to observe something 44 million kilometers across from a distance of about 256 quintillion kilometers away. To put this in perspective, the angular size of Sagittarius A times, as seen from Earth, is approximately 52 micro-arcseconds. An arcsecond is 1/3000, 600th of a degree. A micro-arcsecond is 1/millionth of an arcsecond. To give you a sense of scale, if Sagittarius A times were a donut in New York City, viewing it from Earth would be like standing in Los Angeles and trying to see the individual sprinkles on that donut. Not just seeing the donut, seeing the individual sugar crystals on its surface. No single telescope on Earth or even in space has the resolution to see something so small. The Hubble Space Telescope, one of our most powerful optical telescopes, has a resolution of about 40 milliarcseconds, nearly 1,000 times too coarse to resolve Sagittarius A*'s shadow. We needed something dramatically more powerful. We needed a telescope the size of Earth itself. Obviously, we can't build a physical telescope with a diameter of 13,000 kilometers. The engineering challenges alone would be insurmountable, not to mention the minor detail that most of Earth's surface is covered by oceans. But there's a clever technique in radio astronomy called Very Long Baseline Interferometry, or VLBI for short, that allows us to achieve something almost as good. Here's how VLBI works. Instead of building one giant telescope, you use multiple radio telescopes scattered across vast distances. Each telescope observes the same target at precisely the same time, recording both the incoming radio waves and extremely accurate timestamps using atomic clocks synchronized to GPS. Later, these observations are combined using sophisticated computer algorithms that effectively turn the array of telescopes into a single virtual telescope with a diameter equal to the maximum separation between telescopes. The resolution of a telescope depends on its diameter and the wavelength of light it's observing. The larger the telescope diameter and the shorter the wavelength, the finer the details you can resolve. By creating a virtual telescope with a baseline spanning the Earth and observing at millimeter wavelengths, you can achieve angular resolutions of around 20 micro-arcseconds, just good enough to resolve the shadow of a supermassive black hole. This is the principle behind the Event Horizon Telescope. Not a single instrument, but a planetary-scale array of radio telescopes working in perfect synchronization to achieve the impossible, capturing the first image of a black hole's shadow. Chapter 4. Building an Earth-sized telescope. The Event Horizon Telescope, or EHT, represents one of the most ambitious observational campaigns in the history of astronomy. The concept had been discussed since the early 2000s, but turning it from an idea into reality required solving numerous technical, logistical, and theoretical challenges. Let's explore what it took to build a telescope as large as our planet. First, you need radio telescopes, and not just any radio telescopes, but ones specifically designed to observe at millimeter wavelengths. The EHT observes at a wavelength of 1.3 millimeters, which corresponds to a frequency of 230 gigahertz. Why this particular wavelength? There are several important reasons. At longer wavelengths, the radio emission from Sagittarius A times is scattered by ionized plasma in the interstellar medium between us and the galactic center. This scattering blurs the image, like trying to see clearly through frosted glass. The scattering effect decreases at shorter wavelengths, so millimeter wavelengths allow us to see through this cosmic fog much more clearly. Additionally, the accretion disk around Sagittarius A times emits strongly at millimeter wavelengths, providing a bright backlight against which the black hole shadow can be seen. But observing at millimeter wavelengths comes with its own challenges. Water vapor in Earth's atmosphere absorbs millimeter wave radiation very efficiently. This is why EHT telescopes must be located at high, dry sites where there's less atmospheric water vapor to interfere with observations. The telescopes that participated in the April 2017 observations of Sagittarius A times included some of the most remote and extreme locations on Earth. There was the Atacama Large Millimeter Array in Chile, perched at an altitude of 5,000 meters in one of the driest places on Earth. The South Pole Telescope, located at the Amundsen Scott South Pole Station in Antarctica, where temperatures can drop to minus 73 degrees Celsius, and the thin, dry atmosphere at an altitude of 2,835 meters, provides excellent observing conditions. The Sub-Millimeter Telescope on Mount Graham in Arizona, the IRAM 30-meter telescope in the Spanish Sierra Nevada mountains, the James Clerk Maxwell Telescope and Sub-Millimeter Array in Hawaii, high on the summit of Mauna Kea, the Large Millimeter Telescope in Mexico, and others. Each of these telescopes had to be equipped with extremely sensitive receivers capable of detecting the faint radio signals from the galactic center. These receivers are so sensitive that they can detect changes in power equivalent to a billion billionths of a watt. To achieve such sensitivity, the receivers are cooled to just a few degrees above absolute zero using liquid helium or advanced cryogenic systems. Timing is absolutely critical for VLBI. All the telescopes must observe the target at precisely the same instant, and we need to know exactly when each observation was made. This requires atomic clocks accurate to better than a millionth of a second. Each EHT station uses hydrogen mesa atomic clocks, which are among the most accurate timekeeping devices ever created. These clocks are synchronized using GPS satellites, ensuring that observations made in Chile, Hawaii, Arizona, Spain, and Antarctica are all perfectly aligned in time. The amount of data generated by these observations is staggering. Each telescope records about 64 gigabits of data per second during observations. Over the course of several nights of observing, each station accumulates multiple petabytes of data that's millions of gigabytes. To give you a sense of scale, If you tried to transfer this data over the internet, even with a fast connection, it would take weeks or months. Instead, the data is recorded on special high-capacity hard drives, which are then physically shipped to central processing facilities, a modern version of the old sneakernet method of data transfer. The 2017 observations of Sagittarius A times faced an additional logistical challenge: the South Pole telescope. Antarctica's harsh winter makes it impossible to fly in or out from April through October. The hard drives containing the South Pole data had to wait until the Antarctic summer before they could be shipped out, meaning the complete dataset couldn't be assembled until December 2017, 8 months after the observations were made. Once all the data arrived at the processing centers, primarily MIT Haystack Observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Germany, the real computational challenge began. The data from each telescope had to be carefully correlated, combining the signals to reconstruct what the virtual Earth-sized telescope had observed. This correlation process required a specialized supercomputer consisting of about 800 CPUs connected through a 40 gigabit per second network. But correlation was just the first step. The raw correlated data doesn't give you a picture. It gives you information about the spatial frequencies present in the image, essentially. Information about edges, patterns, and structures. Converting this information into an actual image requires sophisticated imaging algorithms. And here's where things get even more complicated. There are infinitely many possible images that could be consistent with the observed data. This is where the genius of the EHT team's approach becomes apparent. They developed multiple independent imaging pipelines, each using different algorithms and assumptions. Teams worked separately, not sharing their results until all were complete. Only when all teams had produced their images did they compare results. The remarkable finding was that despite using different methods, all the pipelines produced similar images, a ring-like structure with a dark center. This convergence of independent methods gave confidence that the images represented real features of Sagittarius A times, rather than artifacts of any particular imaging algorithm. Chapter 5. The Unique Challenges of Sagittarius A**. While the Event Horizon Telescope had already successfully imaged the supermassive black hole at the center of the galaxy M87 in 2019, Sagittarius A times presented unique challenges that made it far more difficult to image, despite being much closer to Earth. Understanding these challenges helps us appreciate just how remarkable the final image truly is. The first and most significant challenge is variability. The hot plasma in the accretion disk around Sagittarius A times orbits the black hole incredibly fast. For a black hole of 4 million solar masses, orbital periods near the innermost stable circular orbit are on the order of minutes. This means the appearance of Sagittarius A times changes dramatically on timescales of minutes to hours. It's like trying to photograph a restless child. You can't use a long exposure or everything becomes blurred. M87*, despite being 1,000 times more massive than Sagittarius A*, changes much more slowly. Its enormous mass means that orbital timescales near the event horizon are measured in days or weeks. The EHT team could observe M87 times for many hours, building up data over long periods to create a clear image. But Sagittarius A times wouldn't sit still long enough for this approach to work. To solve this problem, the imaging team had to develop entirely new techniques. Rather than trying to create a single long exposure image, they created thousands of short snapshots of Sagittarius A*. each representing a possible state of the system at different moments. Then they used statistical methods to identify which features remained consistent across all these snapshots. The bright ring structure that appears in the final image represents the time-averaged appearance of Sagittarius A, times the features that persist despite the rapid variations in the accretion flow. The second major challenge involves interstellar scattering. Between Earth and the galactic center lies about 27,000 light-years of interstellar space, which is not empty, but filled with a tenuous plasma of ionized gas. Radio waves passing through this plasma get scattered, much like headlights appear to blur and spread out when viewed through fog. This scattering is wavelength dependent. Longer wavelengths scatter more strongly than shorter wavelengths. At the 1.3 mm wavelength used by the EHT, the scattering is minimized, but still significant. The observed size of Sagittarius A times includes contributions both from the intrinsic size of the emission region near the black hole and from this scattering effect. Scientists had to develop sophisticated models of the scattering process to disentangle these two effects. Previous observations at longer wavelengths helped characterize the scattering, allowing the team to correct for it in the EHT data. The imaging team also had to account for the fact that Sagittarius A times is located right in the plane of our galaxy, meaning we're looking through a dense concentration of stars, gas, and dust. This pollution, as astronomers call it, adds noise and complexity to the observations. In contrast, M87 is located in a direction that takes us out of the galactic plane, providing a much cleaner line of sight. There's also the challenge of Earth's rotation. The Event Horizon Telescope is an array of telescopes distributed around the globe, but it's not a uniform or complete array. There are large gaps over the oceans, for instance where no telescopes are located. As Earth rotates during an observing session, the configuration of the array changes continuously. The baselines between different pairs of telescopes trace out different patterns in what's called the UV plane, which determines which spatial scales the array is sensitive to. For Sagittarius A*, the rapid variability means that the array configuration is constantly changing, not just due to Earth's rotation, but also because the source itself is changing. The imaging algorithms had to account for both of these effects simultaneously, keeping track of which baselines were measuring which parts of the variable source at which times. Temperature and weather at the observing sites added further complications. While the sites were chosen for their typically clear, dry conditions, weather is never perfectly predictable. If one telescope is shut down due to weather during part of the observing campaign, that affects the coverage of the UV plane and the overall sensitivity of the array. The team had to carefully design observing schedules to ensure they could obtain usable data even if some stations experienced weather problems. Then there's the computational challenge we mentioned earlier. Processing the Sagittarius A times data required about 5 years of intensive work. Supercomputers ran for months, testing different imaging algorithms, models of the source, and scattering corrections. The team generated not just one image, but thousands of possible images, using each to understand the range of possible appearances consistent with the data and to test the robustness of their results. All of these challenges meant that while the M87 times image was announced in April 2019, the Sagittarius A times image wasn't ready until May 2022, 3 years later. Despite using data from the same 2017 observing campaign, the delay wasn't due to lack of effort, but rather reflected the enormous complexity of extracting a clear image from such difficult data. Chapter 6. The first image. What we saw. On the 12th of May 2022, at simultaneous press conferences held around the world, the Event Horizon Telescope collaboration unveiled the first image of Sagittarius A*. For those who had worked on the project, it was the culmination of decades of effort. For humanity as a whole, it was a historic moment, the first time we had seen the supermassive black hole at the heart of our own galaxy. The image shows a bright ring of emission surrounding a dark central region. The ring has a diameter of approximately 52 micro-arc-seconds as viewed from Earth, which corresponds to a physical size of about 51.8 million kilometers, roughly the distance between the Sun and Mercury. The ring isn't perfectly uniform. It has subtle variations in brightness around its circumference, with some regions appearing slightly brighter than others. The dark center, the black hole's shadow, has a diameter of roughly 52 micro-arc-seconds as well. This dark region is not the event horizon itself, but rather the shadow cast by the event horizon. Due to the extreme bending of space-time near the black hole, light emitted from the accretion disk behind the black hole either escapes to reach us or gets captured by the event horizon. The boundary between these two fates creates the shadow, which appears about 2.5 times larger than the actual event horizon. What makes this image so profound is not just that we can see the shadow, but that we can measure it. The size, shape, and features of the shadow are directly related to fundamental properties of the black hole, particularly its mass and spin. And remarkably, what the EHT observed matches almost perfectly with theoretical predictions made decades ago for what a black hole of approximately 4 million solar masses should look like. The bright ring represents emission from the accretion disk hot plasma, orbiting the black hole at relativistic speeds. The brightness of different parts of the ring tells us about the structure of the accretion flow. Theory predicts that the side of the disk rotating toward us should appear brighter due to relativistic beaming effects, essentially the Doppler effect for light. The EHT image shows exactly this asymmetry, providing powerful confirmation that we're seeing a rapidly rotating accretion disk. One of the most striking aspects of the image is how similar it looks to the earlier image of M87*. Despite M87 times being more than 1,000 times more massive than Sagittarius A*, despite the two black holes being in completely different types of galaxies, M87 is a giant elliptical galaxy, while the Milky Way is a spiral galaxy. And despite their vastly different environments, both black holes show the same essential structure, a bright ring surrounding a dark shadow. This similarity is profound because it suggests that the behavior of matter near event horizons follows universal patterns, regardless of the specific details of each black hole. The image also reveals features that weren't fully expected. The ring shows 3 bright knots, or regions of enhanced emission. These could represent hotspots in the accretion disk, perhaps regions where magnetic fields have become particularly tangled and are efficiently converting gravitational energy into radiation. The presence and location of these bright regions varies on minute-by-minute timescales, which is why the imaging team had to develop their innovative snapshot and average approach. From this single image, or more precisely, from the ensemble of consistent features seen across thousands of snapshot images, scientists can extract an enormous amount of information. By comparing the observed image with simulations run on supercomputers, they can constrain the viewing angle, the inclination at which we're seeing the black hole, the spin of the black hole, the temperature and density of the plasma in the accretion disk, and the strength and structure of magnetic fields threading through that plasma. The analysis suggests that we're viewing Sagittarius A times at a relatively moderate inclination, not face-on and not edge-on, but somewhere in between. The black hole appears to be spinning, and the spin is likely in the same direction as the orbital motion of the accretion disk, what astronomers call prograde, spin, rather than retrograde. The plasma in the accretion disk is extraordinarily hot, with temperatures reaching billions of degrees. Yet, paradoxically, the density is quite low. The region near the event horizon is far more empty than the air you're breathing right now. Chapter 7. How big is it really? Now we come to the central question. Exactly how big is Sagittarius A*? The answer depends on which dimension we're measuring, because a black hole has several characteristic sizes, each with different physical meanings. Let's start with the event horizon itself. For a non-rotating black hole, the radius of the event horizon is given by the Schwarzschild radius, named after Karl Schwarzschild, who first derived this solution. The Schwarzschild radius depends only on the black hole's mass and is given by the formula R equals 2gm divided by c squared, where g is the gravitational constant, m is the mass, and c is the speed of light. For Sagittarius A*, with a mass of 4.3 million solar masses, this calculation gives a Schwarzschild radius of approximately 12.7 million kilometers. The diameter of the event horizon is therefore about 25.4 million kilometers. To put this in context, that's about 18 times the diameter of our Sun, which is about 1.4 million kilometers. If you could somehow place Sagittarius A times in our solar system, the event horizon would fit comfortably within Mercury's orbit, which ranges from 46 to 70 million kilometers from the Sunday. But Sagittarius A times is not a simple non-rotating black hole. Like most astrophysical black holes, it's almost certainly spinning. A spinning black hole, described by the Kerr metric, named after mathematician Roy Kerr, has a slightly smaller event horizon than a non-rotating black hole of the same mass. The event horizon radius depends on both the mass and the spin of the black hole. For a maximally spinning black hole, the event horizon radius can be as small as half the Schwarzschild radius. Current best estimates suggest Sagittarius A times is indeed spinning, though probably not at the maximum possible rate. The EHT observations, combined with decades of other observations, suggest the black hole is rotating with a dimensionless spin parameter between 0.4 and 0.9, where 0 represents no spin and 1 represents maximum spin. This means the actual event horizon is probably somewhat smaller than the simple Schwarzschild calculation would suggest, perhaps around 20 to 22 million kilometers in diameter. The next important size is the innermost stable circular orbit, or ISCO. This is the smallest radius at which matter can orbit the black hole in a stable circular orbit. Inside the ISCO, orbits become unstable. Any perturbation will cause the orbiting matter to either spiral inward and cross the event horizon or be flung outward. For a non-rotating black hole, the ISCO is located at 3 times the Schwarzschild radius. For a spinning black hole, the ISCO can be much closer. For a maximally spinning black hole rotating in the same direction as the orbit, the ISCO can be as close as the event horizon itself. The ISCO is important because it marks the inner edge of the accretion disk. Matter can orbit stably outside the ISCO, gradually spiraling inward due to friction and viscosity. But once matter crosses the ISCO, it's on a one-way trip to the event horizon. The bright ring we see in the EHT image likely corresponds to emission coming from near the ISCO, where the accretion disk is hottest and brightest. For Sagittarius A asterisk, the ISCO is probably located at a radius of 30 to 40 million kilometers, depending on the exact spin of the black hole. This matches well with the observed size of the bright ring in the EHT image. The third important size is the photon sphere, also called the photon orbit or light ring. This is the radius at which light itself can orbit the black hole. At this precise radius, space-time is so curved that a photon traveling perpendicular to the radial direction will follow a circular path around the black hole. For a non-rotating Schwarzschild black hole, the photon sphere is located at exactly 1.5 times the Schwarzschild radius, or about 19 million kilometers, for Sagittarius A asterisk. For a spinning Kerr black hole, there are actually two photon spheres, one for photons orbiting in the same direction as the black hole's spin, and one for photons orbiting in the opposite direction. These orbits are unstable. Any slight perturbation will cause a photon to either fall into the black hole or escape to infinity. The photon sphere is crucial for understanding the black hole shadow we see in the EHT image. Light emitted from just inside the photon sphere gets trapped and falls into the black hole. Light emitted from just outside the photon sphere can escape. This creates a sharp boundary in the image, the edge of the shadow. Due to various general relativistic effects, including gravitational lensing, the shadow appears larger than the photon sphere itself, typically about 2.5 to 2.6 times the radius of the event horizon. This is exactly what the EHT observed. The shadow of Sagittarius A times has a diameter of about 52 micro-arcseconds. Given the distance to the galactic center of approximately 26,000 light-years, recent measurements suggest it might be slightly closer than the often quoted 27,000 light-years. This angular size corresponds to a physical diameter of roughly 51.8 million kilometers. This matches beautifully with theoretical predictions for a black hole of 4.3 million solar masses. But there's yet another size we should consider: the radius of influence of the black hole. This is the region within which the black hole's gravity dominates over the gravitational influence of surrounding stars. Beyond this radius, the collective gravity of all the stars in the galactic bulge becomes more important than the black hole's gravity. For Sagittarius A asterisk, the radius of influence is approximately 3 light-years, or about 28 trillion kilometers. This is the region within which stars orbit primarily around the black hole rather than around the general galactic center. The measurements from the EHT are precise to about 20%, which might not sound impressive at first, but consider what we're doing: measuring the size of an object smaller than Mercury's orbit from a distance of 26,000 light-years. 20% precision under these circumstances represents an extraordinary achievement. It's equivalent to measuring the size of a tennis ball on the Moon from Earth. More importantly, these measurements agree with predictions from general relativity to within the measurement uncertainties. If Sagittarius A times were not a black hole, if it were some other exotic object like a boson star, a fermion ball, or any of the other theoretical alternatives that have been proposed, it would likely produce a different shadow size or shape. The fact that observations match black hole predictions so well provides powerful evidence that we really are seeing the signature of an event horizon. Chapter 8. The Physics of the Shadow. To truly understand what the EHT image reveals, we need to delve deeper into the physics of how light behaves near a black hole. This is where Einstein's general relativity becomes not just abstract mathematics, but a concrete tool for predicting observable phenomena. In flat spacetime, the kind of spacetime that exists far from any massive objects, light travels in straight lines. This is such a fundamental part of our everyday experience that we rarely think about it. When you look at a distant object, the light from that object has traveled to your eye along a straight path. But near a massive object, space-time is curved, and light must follow the curves of spacetime. We call these curved paths null geodesics, paths that light rays follow through curved spacetime. Near a black hole, space-time curvature becomes extreme. Light rays passing close to the event horizon are bent through large angles. Some light rays that are aimed slightly away from the black hole can be bent so severely that they actually loop around the black hole one or more times before escaping. This creates multiple images of objects located behind the black hole, a phenomenon called gravitational lensing. The photon sphere represents the ultimate limit of this lensing effect. At exactly the photon sphere radius, light can orbit the black hole indefinitely. Though this orbit is unstable, any infinitesimal disturbance will cause the photon to either fall in or escape. This unstable photon orbit is what creates the sharp edge of the black hole shadow. Here's how it works. Imagine you're looking at a black hole with a glowing accretion disk behind it. Light from the backside of the accretion disk travels toward you, but some of this light passes very close to the black hole. If a light ray passes just outside the photon sphere, it gets bent severely, but can still escape, reaching your eye. This light appears to come from very close to the edge of the black hole. If a light ray passes just inside the photon sphere, it gets captured and falls into the black hole, never reaching you. This creates a bright ring at the edge of the shadow. Photons that orbit near the photon sphere before escaping create a concentration of brightness at the shadow's edge. In fact, there's a whole series of images. The first-order image from photons that go around the black hole once, a second-order image from photons that go around twice, a third-order image from photons that go around 3 times, and so on. Each successive image is fainter and appears closer to the edge of the shadow. The infinite sum of all these images creates what theorists call the photon ring, a bright feature that should appear at precisely the edge of the black hole shadow. The EHT observations at 1.3 millimeters don't have quite enough resolution to separate the photon ring from the emission from the accretion disk itself. The bright ring we see in the image is a combination of the photon ring and emission from the hot plasma orbiting near the ISCO. Future observations with additional telescopes and at shorter wavelengths may be able to resolve these different components, potentially providing even more stringent tests of general relativity. One of the most fascinating aspects of the shadow is that its size and shape depend on the black hole's mass and spin in a predictable way. A more massive black hole creates a larger shadow. A spinning black hole creates a shadow that's slightly distorted, not perfectly circular, but slightly flattened in one direction. By carefully measuring the size and shape of the shadow, we can determine not just that we're looking at a black hole, but also measure some of its fundamental properties. The EHT observations of Sagittarius A times show a shadow that's very close to circular, though with the measurement uncertainties, a small amount of flattening can't be ruled out. The size of the shadow, as we've discussed, agrees well with predictions for a black hole of 4.3 million solar masses. These measurements provide direct confirmation that general relativity accurately describes spacetime, even in the extreme environment near an event horizon. But there's something even more subtle happening in the image. Due to a phenomenon called relativistic beaming, or Doppler boosting, the side of the accretion disk moving toward us appears brighter than the side moving away. This happens because the orbiting plasma is moving at a significant fraction of the speed of light. When a source is moving toward you at relativistic speeds, the light you receive is blue-shifted to higher frequencies and energies, and the apparent brightness is enhanced. When the source is moving away, the opposite happens, redshift and dimming. For an accretion disk, viewed at an angle, not face-on, one side is always moving toward us, and one side is moving away. This creates an asymmetry in the brightness of the ring. In the EHT image of Sagittarius A*, we can see hints of this asymmetry, with some parts of the ring appearing brighter than others. By analyzing the pattern of this brightness variation, scientists can deduce information about the rotation of the accretion disk and potentially about the spin of the black hole itself. There's also the phenomenon of gravitational redshift to consider. Light climbing out of a deep gravitational potential well loses energy, shifting to longer wavelengths. For light emerging from near the event horizon of a supermassive black hole, this redshift can be substantial. A photon emitted at a particular frequency near the event horizon will be observed at a significantly lower frequency by the time it reaches Earth. This affects the spectrum of light we observe from the accretion disk and must be accounted for when interpreting the observations. All of these effects, gravitational lensing, photon rings, Doppler boosting, gravitational redshift, combine to create the complex image we see. The EHT image is not just a pretty picture. It's a detailed map of how space-time is warped near the event horizon of a supermassive black hole. A direct visualization of Einstein's equations in their most extreme regime. Chapter 9. Comparing the two black holes. The Event Horizon Telescope has now imaged two supermassive black holes, M 87 times and Sagittarius A*. While both images show the characteristic ring and shadow structure, comparing these two systems reveals fascinating insights about black hole physics and highlights just how remarkable the Sagittarius A times observations truly are. M 87 times resides at the center of Messier 87, a giant elliptical galaxy located about 55 million light-years from Earth in the Virgo galaxy cluster. This black hole is a true monster, containing approximately 6.5 billion solar masses, about 1,500 times more massive than Sagittarius A*. Despite being much farther away than Sagittarius A*, M 87*, enormous mass makes it appear almost the same angular size in our sky. The shadow of M 87 times subtends about 40 microarcseconds compared to 52 microarcseconds for Sagittarius A*. The first and most obvious difference between the two systems is their behavior over time. M 87 times is relatively stable. You can observe it for hours or even days, and its appearance changes slowly, if at all. This made imaging M 87 times challenging but ultimately straightforward. Long integration times could be used to build up high signal-to-noise data, and standard imaging techniques could be applied. Sagittarius A*, as we've discussed, is a completely different beast. It changes on timescales of minutes. During a single observing night, the bright spots in the accretion disk can move, appear, and disappear. This variability is a direct consequence of the much smaller mass. The characteristic timescale for phenomena near a black hole scales linearly with mass. M87 times is 1,500 times more massive, so processes that take minutes around Sagittarius A times take days around M87 *. This difference in variability reflects fundamental physics. The hot plasma orbiting near the event horizon moves at speeds approaching the speed of light. The time it takes for this plasma to complete an orbit depends on the orbital radius and the mass of the black hole. For Sagittarius A *, material orbiting near the ISCO completes an orbit in roughly 20 minutes. For M87 *, the equivalent orbit takes about a month. Despite these dramatic differences in mass, distance, and temporal behavior, both black holes show remarkably similar ring structures in their images. The diameter of the shadow, when measured in units of the Schwarzschild radius, is almost identical for both black holes. This provides powerful evidence that the shadow we're seeing is indeed a universal feature of black holes, a signature of the event horizon itself, rather than details specific to any particular system. However, there are also intriguing differences. The brightness asymmetry in the ring, the pattern of bright and faint regions differs between the two black holes. M87 times shows a pronounced bright spot on one side of the ring, likely representing a combination of Doppler boosting and the structure of the accretion flow. Sagittarius A times shows a more complex pattern with multiple bright regions. These differences likely reflect differences in how matter is accreting onto the two black holes. M87 times is actively accreting matter at a relatively high rate and produces a powerful jet, a collimated beam of plasma that shoots out from near the black hole at nearly the speed of light, extending for thousands of light years. This jet is visible in radio images of M87 and is one of the most spectacular structures in extragalactic astronomy. Sagittarius A *, in contrast, is what astronomers call quiescent. It's accreting matter at a very low rate, only about 1 Earth mass per year, which for a supermassive black hole is virtually nothing. It doesn't produce a powerful jet, though there is evidence for weak outflows. The low accretion rate means that Sagittarius A times is far dimmer than it would be if it were actively feeding. In fact, Sagittarius A times is one of the dimmest supermassive black holes known, given its mass. This quiescent state actually makes Sagittarius A times more challenging to observe. There's less emission to work with, which means longer integration times are needed to achieve a given signal-to-noise ratio. Combined with the rapid variability, this means the EHT team had to extract maximum information from relatively short snapshots of a faint, flickering source. The viewing angle, the inclination at which we see the system, also appears to differ between M87 times and Sagittarius A *. M87 times seems to be viewed at a fairly high inclination, meaning we're looking at the accretion disk and jet at an angle rather than face-on. Sagittarius A times appears to be viewed at a more moderate inclination. These different viewing angles affect the appearance of the ring and the prominence of various relativistic effects. Despite these differences, the fundamental success of the EHT in imaging both systems demonstrates the power of the technique. The fact that the same array of telescopes, using the same observing wavelength and similar data processing techniques, can successfully image black holes that differ by a factor of 1,500 inches mass and 2,000 inches distance, shows that we've truly developed a general-purpose tool for studying event horizons. Chapter 10. What the size tells us about general relativity. The measurement of Sagittarius A asterisk size is more than just a number. It's a test of Einstein's general theory of relativity in one of the most extreme environments in the universe. To understand why this matters, we need to think about what general relativity actually predicts and how we can test whether those predictions are correct. Einstein's field equations relate the curvature of space-time to the distribution of mass and energy. These equations have been tested extensively in the solar system and with binary pulsar systems, and they've passed every test with flying colors. But the gravity near Earth, or even near the Sun, or even near a pulsar, is weak compared to the gravity near a black hole event horizon. The question is, does general relativity still work when gravity becomes this strong? The answer, based on the EHT observations, appears to be yes. The size and shape of the Sagittarius A times shadow match general relativistic predictions to within the measurement uncertainties. This is non-trivial. Alternative theories of gravity modifications to general relativity proposed for various theoretical reasons often predict different shadow sizes or shapes. By measuring the shadow and finding that it matches Einstein's predictions, we're ruling out a whole class of alternative theories. For example, some modified gravity theories predict that there might not be a true event horizon. Instead, there might be a surface, a solid or quasi-solid boundary, at or near where the event horizon should be. If such a surface existed, light could reflect off it, and the shadow would look different. The EHT observations see no evidence for such a surface. The dark region in the center of the image is truly dark, consistent with the presence of an event horizon from which no light escapes. Other alternative theories predict that the relationship between a black hole's mass and its shadow size might be different from what general relativity predicts. Some theories predict larger shadows. Some predict smaller shadows. The EHT measurement of a shadow size consistent with 4.3 million solar masses, a mass independently determined from stellar orbits, rules out large classes of these alternatives. The near-circular shape of the shadow is also significant. A perfectly spherical, non-rotating black hole should cast a perfectly circular shadow. A rotating black hole should cast a slightly elliptical shadow, with the degree of ellipticity depending on the spin and viewing angle. The Sagittarius A times shadow appears very close to circular, which constrains how fast the black hole can be spinning and what angle we're viewing it from. But perhaps the most profound test comes from comparing the black hole's mass determined from stellar orbits with the mass inferred from the shadow size. The stellar orbit method uses Newtonian gravity, or more precisely, post-Newtonian corrections to Newtonian gravity, which are the weak field limit of general relativity. This method tells us there's something with a mass of 4.3 million suns at the galactic center. The EHT shadow measurement uses strong field general relativity, Einstein's equations, in their full non-linear glory, with space-time curved to the breaking point. This method tells us the shadow size corresponds to a black hole of 4.3 million solar masses. The fact that these two completely independent measurements, using completely different physical regimes, agree so well is powerful evidence that general relativity is correctly describing gravity across the entire range from weak to strong fields. This type of consistency check is exactly what physicists look for when validating theories. It's not enough for a theory to explain one type of observation. A truly correct theory should explain all observations using the same fundamental equations. General relativity is passing this test with flying colors. The EHT observations also provide tests of general relativity that are complementary to other strong field tests, like gravitational wave observations from merging black holes. LIGO and Virgo detect gravitational waves from stellar mass black holes, roughly 10 to 100 solar masses, during the brief moments when they're merging highly dynamical, violent events. The EHT observes supermassive black holes, millions to billions of solar masses, in relatively steady states, static, or slowly evolving configurations. These different types of observations test different aspects of general relativity. Gravitational wave observations test how space-time responds to rapid, large amplitude disturbances. Black hole shadow observations test the structure of space-time near a stationary event horizon. The fact that general relativity successfully describes both situations strengthens our confidence in the theory. There's still room for surprises, of course. The measurement uncertainties in the EHT observations are about 20%, which leaves some wiggle room for small deviations from general relativity. Future observations with better resolution and sensitivity might reveal subtle differences from Einstein's predictions. If such differences were found, they would be revolutionary evidence for new physics beyond general relativity. But for now, the message is clear. Einstein was right, even in the most extreme gravitational environment we can observe. The space-time around Sagittarius A times behaves exactly as the century-old equations of general relativity predict. Chapter 11: The accretion disk and plasma physics. While the shadow itself provides tests of general relativity, the bright ring surrounding the shadow tells us about the physics of how matter behaves in extreme conditions. The plasma swirling around Sagittarius A times exists in a state unlike anything we can create on Earth, hotter than the cores of stars, more tenuous than the best laboratory vacuums, threaded with powerful magnetic fields, and moving at relativistic speeds. Understanding this plasma requires combining general relativity with magnetohydrodynamics, the physics of electrically conducting fluids in magnetic fields. This combination, called general relativistic magnetohydrodynamics, or GRMHD for short, is computationally challenging. The equations are non-linear, meaning different effects couple together in complex ways. Solving these equations requires massive supercomputers running for weeks or months. The EHT team, in parallel with analyzing their observations, ran extensive GRMHD simulations of black hole accretion. These simulations start with theoretical models of how gas behaves near a black hole and calculate what the resulting image should look like. By comparing simulated images with actual observations, scientists can constrain the properties of the plasma and the magnetic fields. One of the key questions is, what's heating the plasma? Material falling into a black hole converts gravitational potential energy into kinetic energy. It speeds up as it falls. But kinetic energy of ordered motion doesn't directly produce light. Something has to convert this ordered motion into random thermal motion heat, and then that heat has to be radiated away as light. In accretion disks, several heating mechanisms are thought to be important. Viscous friction, where different parts of the disk moving at different speeds rub against each other, converts kinetic energy into heat. Magnetic reconnection, where tangled magnetic field lines suddenly snap and reconfigure, can release enormous amounts of energy in small regions, heating the plasma to extreme temperatures. Turbulence, driven by various instabilities in the disk, mixes the plasma and generates heat. The relative importance of these different mechanisms affects the appearance of the accretion disk. A disk where heating is dominated by viscous processes looks different from one where magnetic reconnection is dominant. By comparing observations with simulations that include different heating mechanisms, scientists can infer which processes are actually operating around Sagittarius A*. The magnetic fields threading through the accretion disk play a crucial role. These fields aren't just passive, they actively shape how the plasma behaves. Magnetic pressure can support the plasma against gravity, preventing it from collapsing. Magnetic tension can extract energy from the rotational motion of the disk, transporting angular momentum outward and allowing matter to spiral inward toward the black hole. There's also the possibility that magnetic fields launch outflows or jets. While Sagittarius A times doesn't have a powerful jet like M87*, there's evidence for weak outflows, plasma being blown away from the black hole, rather than falling in. These outflows might be driven by magnetic forces, with field lines acting like slingshots to fling material outward. Understanding these outflows is important because they represent a way that black holes can influence their surroundings, potentially affecting the evolution of the entire galaxy. The temperature of the plasma in the inner accretion disk is estimated to be around 10 billion degrees Kelvin, nearly 1,000 times hotter than the core of the Sunday. At such temperatures, the plasma is fully ionized, with electrons stripped completely from atomic nuclei. The electrons have enormous kinetic energies, moving at speeds close to the speed of light. This creates what physicists call a relativistic plasma, where you can't use the ordinary equations of thermodynamics, but must account for special relativistic effects. Interestingly, despite these extreme temperatures, the density of the plasma is incredibly low. The number density of particles near the event horizon is estimated to be around 1 million particles per cubic centimeter. That might sound like a lot, but for comparison, air at sea level contains about 19 particles per cubic centimeter, 100 trillion times denser. The plasma around Sagittarius A times is better vacuum than anything we can create in a laboratory, yet it's hot enough to glow brightly at millimeter wavelengths. This combination, extremely hot but extremely tenuous, creates interesting physics. The plasma is what physicists call collisionless. Particles almost never actually collide with each other. Instead, they interact through long-range electromagnetic forces. This changes how energy is distributed and how the plasma radiates. Understanding collisionless plasmas in curved spacetime remains an active area of research, with important implications for interpreting the EHT observations. The radiation we see from the accretion disk is primarily synchrotron radiation light produced when relativistic electrons spiral in magnetic fields. As an electron spirals around a magnetic field line, it accelerates, centripetal acceleration, and accelerating charges radiate electromagnetic waves. The frequency of this radiation depends on the electron's energy and the strength of the magnetic field. For the EHT observations at 1.3 millimeters, we're seeing synchrotron radiation from electrons with energies of a few billion electron volts in magnetic fields of around 10 Gauss, about 10,000 times stronger than Earth's magnetic field. But the story doesn't end with synchrotron emission. High-energy photons passing through the plasma can interact with electrons through a process called inverse Compton scattering. A photon collides with a relativistic electron and gets boosted to much higher energy. This process can shift photons from millimeter wavelengths up to X-ray wavelengths. Observations of Sagittarius A times at X-ray wavelengths, using space telescopes like Chandra and xmm, show occasional flares, brief brightenings that last for hours. These flares are thought to be produced when magnetic reconnection events suddenly heat electrons to even higher energies, producing a burst of inverse Compton X-rays. Chapter 12. The stars that orbit Sagittarius A**. While the EHT observations provided the first direct image of Sagittarius A**, much of what we know about this black hole comes from decades of painstaking observations of stars orbiting around it. These stellar orbits provide complementary information to the EHT image and play a crucial role in confirming the black hole's mass and properties. The story of these observations is itself remarkable. In the early 1990 seconds, Reinhard Genzel's team in Germany and Andrea Ghezi's team in the United States independently began programs to track individual stars in the crowded region near the galactic center. At the time, this was considered nearly impossible. The stars are extraordinarily faint. Many are around magnitude 16 or 17, requiring large telescopes to see at all. They're packed densely together, making it hard to distinguish individual stars, and Earth's atmosphere blurs the images, washing out fine details. The breakthrough came with adaptive optics technology. Earth's atmosphere is constantly churning, creating turbulence that causes starlight to twinkle and distorts images. Adaptive optics uses a deformable mirror that changes shape hundreds of times per second, compensating for atmospheric distortions in real time. With adaptive optics, ground-based telescopes can achieve image sharpness comparable to space telescopes, at least for infrared observations where atmospheric turbulence is less severe. Using adaptive optics on large telescopes, the European Southern Observatory's Very Large Telescope in Chile for Genzel's team and the Keck telescopes in Hawaii for Ghezi's team, these researchers began tracking stars with unprecedented precision. They could measure stellar positions to within a few hundred micro-arc seconds, comparable to measuring the width of a human hair seen from a kilometer away. Over years, and then decades, patterns emerged. Individual stars could be tracked as they moved against the background, following clear orbital paths around an invisible massive object at the position of Sagittarius A**. Some stars have orbital periods of decades, allowing their full orbits to be mapped. Others have shorter periods, with the star S2, also called S0-2, being particularly important. S2 is a young, bright star of spectral type B. It has a mass of about 15 times the mass of the Sun and is roughly 100,000 times more luminous. Despite being 26,000 light-years away, it's bright enough to be tracked with extraordinary precision. Most importantly, S2 has an orbital period of only 16 years, meaning researchers have now observed it complete more than 2 full orbits since observations began. The orbit of S2 is highly elliptical. Its distance from Sagittarius A times varies from about 17 light-hours at closest approach to about 100 light-hours at its farthest point. When S2 is at closest approach, called periastron, it's moving at about 2.5% of the speed of light. These extreme conditions make S2 an ideal laboratory for testing general relativity. In 2018, S2 passed through periastron, offering a unique opportunity for detailed observations. Multiple telescopes around the world coordinated to track S2 during this close approach, measuring not just its position, but also its spectrum, the distribution of light across different wavelengths. The spectrum revealed something remarkable. The characteristic wavelength of light from S2 was shifted toward longer, redder wavelengths, exactly as general relativity predicts. This gravitational redshift occurs because light climbing out of a gravitational well loses energy. A photon emitted from S2 when it's deep in Sagittarius A*'s gravitational potential must expend energy to escape, arriving at Earth with a longer wavelength than when it was emitted. The amount of redshift depends on the depth of the gravitational potential, which in turn depends on the mass of the black hole and the star's distance from it. The observed redshift matched general relativistic predictions to within the measurement uncertainties, providing strong confirmation that Sagittarius A times is indeed a supermassive black hole, and that general relativity correctly describes the gravitational field in this extreme environment. This observation, combined with the overall orbital motion of S2 and other stars, allowed Genzel and Gez's teams to determine the mass of Sagittarius A times with remarkable precision, 4.297 million solar masses, with an uncertainty of only about 0.012 million solar masses. But S2 isn't the only star of interest. Astronomers have now tracked hundreds of stars in the galactic center region. Some, like S4, S8, S12, S14, and S17, have well-defined orbits that provide additional constraints on the black hole's mass and position. Others are being tracked, but haven't completed full orbits yet, so their orbital parameters aren't fully determined. Recently, an even more exciting star has been discovered, S4714. This star has an extraordinarily eccentric orbit that may bring it even closer to Sagittarius A times than S2, reaching a distance of only about 12 light-hours at periastron. At its closest approach, S4714 is moving at about 8% of the speed of light. Observing this star during its close approaches will provide even more stringent tests of general relativity and potentially reveal additional details about the environment near the black hole. The orbital observations also provide information about Sagittarius A**'s spin. As a massive spinning object, the black hole drags space-time around with it, an effect called frame dragging, or the Lense-Thirring effect. This dragging causes the orbits of nearby stars to precess. The orientation of each elliptical orbit slowly rotates over time. The rate of precession depends on the black hole's spin. By carefully measuring the precession of stellar orbits, particularly S2, astronomers hope to determine not just that Sagittarius A times is spinning, but how fast it's spinning. Current observations suggest that the precession of S2's orbit is consistent with general relativistic predictions and indicates that Sagittarius A times is likely spinning, though the exact spin parameter isn't yet tightly constrained. Future observations, particularly of S2's next periastron passage in 2026, should provide more precise measurements. The combination of stellar orbit observations and the EHT image provides a remarkably complete picture of Sagittarius A**. The stellar orbits tell us the mass and location of the black hole with exquisite precision. The EHT image confirms that the object casting this gravitational influence has the characteristic shadow of a black hole event horizon. Together, these observations provide overwhelming evidence that Sagittarius A times is a supermassive black hole, exactly as theory predicts. Chapter 13: The Formation and Evolution of Supermassive Black Holes. Now that we know what Sagittarius A times is and how big it is, we can ask deeper questions. Where did it come from? How did a black hole containing 4 million suns form in the first place? And what does its existence tell us about the history of our galaxy? These questions touch on one of the most active areas of research in astrophysics: understanding how supermassive black holes form and grow. Despite decades of study, many aspects of this process remain mysterious. What we do know is that supermassive black holes are ubiquitous. Nearly every large galaxy appears to have one at its center. This suggests that supermassive black hole formation is a natural part of galaxy evolution, not a rare accident. There are several proposed mechanisms for forming supermassive black holes. The most straightforward idea is that they grow from stellar mass black holes. When a massive star exhausts its nuclear fuel and its core collapses, it can form a black hole of perhaps 10 to 100 solar masses. If this black hole finds itself in a dense environment with plenty of gas and stars nearby, it can grow by accreting material and by merging with other black holes. The problem with this scenario is time. To grow from a stellar mass black hole to a supermassive black hole requires gaining millions of solar masses. Even if the black hole is accreting matter at the maximum possible rate, a limit called the Eddington limit, where radiation pressure from the hot accretion disk balances gravity and prevents more matter from falling in it, would take hundreds of millions to billions of years to grow to supermassive size. This might seem like plenty of time after all. The universe is nearly 14 billion years old. But observations of distant quasars, the brilliant active galactic nuclei powered by supermassive black holes, have found billion solar mass black holes existing when the universe was less than a billion years old. These black holes apparently grew to supermassive size remarkably quickly, leaving little time for gradual growth from stellar mass seeds. This has led theorists to propose alternative formation scenarios. Perhaps supermassive black holes don't start from stellar mass seeds at all. Perhaps they form directly from the collapse of massive clouds of gas in the early universe. Under the right conditions, if the gas is very hot and doesn't fragment into stars, a massive gas cloud could collapse directly to form a black hole of thousands or even hundreds of thousands of solar masses. Such an intermediate mass black hole would have a head start and could potentially grow to supermassive size more quickly. Another intriguing possibility involves dense star clusters. In the densely packed cores of young galaxies, stars might collide and merge, building up more massive stars. There's a limit to how massive a star can be. Above about 150 to 300 solar masses, a star becomes unstable. But perhaps in the extreme conditions of the early universe, even more massive objects could form through stellar collisions. When these supermassive stars eventually collapsed, they would form intermediate mass black holes that could serve as seeds for supermassive black holes. Yet another scenario involves black hole mergers. When two galaxies collide and merge, a common occurrence in the universe's history, their central supermassive black holes gradually sink toward the center of the merged galaxy through a process called dynamical friction. Eventually, the two black holes form a binary system, orbiting each other while emitting gravitational waves. The gravitational waves carry away energy and angular momentum, causing the orbit to shrink until the black holes merge into a single, more massive black hole. Sagittarius A times has almost certainly grown through multiple mechanisms over the Milky Way's history. The galaxy is about 13 billion years old, providing plenty of time for growth. Sagittarius A times has likely accreted gas from the interstellar medium, consumed stars that wandered too close, and possibly merged with smaller black holes from satellite galaxies that were cannibalized by the Milky Way over billions of years. What's interesting about Sagittarius A times is that it's currently in a very quiet state. As we mentioned earlier, It's accreting matter at an extremely low rate, only about 1 Earth mass per year. This is far below the Eddington limit. In fact, Sagittarius A times is so underluminous, so much dimmer than it could be if it were actively feeding, that it suggests the supply of gas in the galactic center is currently very limited. But this hasn't always been the case. Evidence suggests that Sagittarius A times was much more active in the relatively recent past. In 2010, astronomers discovered enormous bubbles of gamma-ray emitting gas, extending 25,000 light-years above and below the galactic plane, the so-called Fermi bubbles, named after the Fermi Gamma-Ray Space Telescope that discovered them. These bubbles appear to be the remnants of a massive energy release from the galactic center, possibly from a period when Sagittarius A times was actively accreting and blowing powerful winds or jets. The age of the Fermi bubbles is estimated to be a few million years, suggesting that Sagittarius A times was much more active in the very recent past by astronomical standards. What caused this burst of activity? Perhaps a gas cloud or small galaxy fell into the galactic center, providing a temporary feast for the black hole. Or perhaps the activity is quasi-periodic, with Sagittarius A times going through cycles of active feeding and quiet periods. Looking further back in time, there's evidence that the Milky Way went through more dramatic changes. The galaxy has consumed numerous smaller satellite galaxies over its history, events that would have dumped gas and stars into the galactic center, potentially triggering intense periods of black hole growth. The current stellar population around Sagittarius A times shows signs of bursts of star formation occurring a few million years ago, again suggesting episodic activity. The mass of Sagittarius A times 4.3 million solar masses places it at the lower end of the supermassive black hole mass spectrum. The most massive black holes known contain tens of billions of solar masses. The black hole at the center of the giant elliptical galaxy M87, for instance, is about 1,500 times more massive than Sagittarius A asterisk. The fact that the Milky Way has a relatively modest supermassive black hole is consistent with the galaxy's size and mass. There's a well-established correlation between a galaxy's total mass, or more, specifically, the mass of its central bulge and the mass of its central black hole. This correlation is one of the most intriguing discoveries in modern astrophysics. Why should the mass of a black hole, which contains only a tiny fraction of the galaxy's total mass and influences only a small region at the galaxy's center, be so tightly correlated with properties of the entire galaxy? This suggests that black holes and their host galaxies somehow co-evolve, influencing each other's growth over cosmic time. One proposed mechanism for this co-evolution involves feedback. When a supermassive black hole is actively accreting, it releases enormous amounts of energy, not just light, but also powerful winds and jets. This energy heats the surrounding gas, preventing it from cooling and forming stars. It can even blow gas completely out of the galaxy. This AGN feedback, where AGN stands for Active Galactic Nucleus, provides a self-regulating mechanism. The black hole grows by accreting gas. The accretion releases energy that heats and expels gas. The reduced gas supply throttles the black hole's growth. Sagittarius A asterisk, in its current quiet state, isn't providing significant feedback to the galaxy. But during more active periods in the past, it might have played a role in regulating star formation in the galactic center, shaping the galaxy's evolution in subtle but important ways. Chapter 14. What happens at the event horizon? We've talked extensively about the event horizon, the boundary of no return surrounding a black hole. But what exactly happens at this boundary? And more intriguingly, what lies beyond it? These questions take us to the edge of our understanding, where general relativity meets quantum mechanics, and where certainty gives way to speculation. From the perspective of someone watching from a safe distance, the event horizon is the surface beyond which nothing can escape. If you throw an object toward a black hole and it crosses the event horizon, you will never see or hear from it again. Light signals can't escape from inside the horizon to reach you. This makes the event horizon a one-way membrane in space-time. Things can go in, but nothing comes out. But here's something subtle. From the outside, you never actually see anything cross the event horizon. As an object falls toward the horizon, several relativistic effects combine to make it appear to slow down, freeze, and fade away. Time dilation causes the object's clock to run slower and slower as seen by distant observers. Light from the object becomes increasingly red-shifted, shifting to longer and longer wavelengths until it fades into invisibility. The object appears to asymptotically approach the horizon, never quite reaching it from the external perspective. However, for the infalling object itself, the experience is completely different. An astronaut falling into Sagittarius A times, equipped with an indestructible spacesuit, for the sake of this thought experiment, would notice nothing special upon crossing the event horizon. There's no physical barrier, no wall or surface. The event horizon is simply a place in space-time with particular mathematical properties. The astronaut would sail right through, heading inexorably toward the singularity at the center. Actually, the astronaut's experience wouldn't be quite so pleasant. Long before reaching the event horizon, they would encounter tidal forces, differences in gravitational pull between their head and feet, assuming they're falling feet first. These tidal forces stretch objects along the radial direction while compressing them perpendicular to it, an effect whimsically called spaghettification by physicists. For a stellar mass black hole, tidal forces become lethal well outside the event horizon. But for a supermassive black hole, like Sagittarius A*, the tidal forces at the event horizon are surprisingly mild. The event horizon is so large that the curvature of space-time, while extreme by astronomical standards, isn't extreme compared to the size of a human body. An astronaut could, in principle, survive crossing the event horizon and would have several seconds before tidal forces became unbearable. Of course, this is all academic. Long before reaching the event horizon, the astronaut would be incinerated by the radiation from the accretion disk and torn apart by the turbulent plasma. But it's a useful thought experiment for understanding the geometry of space-time near a black hole. What happens after crossing the horizon? According to general relativity, all paths lead inevitably to the singularity, the point at the center where curvature becomes infinite and the theory breaks down. At the singularity, density becomes infinite, space-time curvature becomes infinite, and our equations stop making sense. This is a sign that general relativity is incomplete. We need a theory of quantum gravity, a theory that combines general relativity with quantum mechanics to understand what really happens at the singularity. Several candidates for quantum gravity have been proposed: string theory, loop quantum gravity, and other approaches attempt to describe gravity at the quantum level. These theories suggest that the classical singularity might be replaced by some kind of quantum structure, perhaps a region of extremely curved but not infinite space-time. perhaps something stranger. But without experimental evidence, we can't know which, if any, of these theories is correct. There's also the question of what the interior of a black hole looks like, if anyone could see it. In the exterior, space and time behave normally. Space is where you can move around. Time is what flows forward. But inside the event horizon, the roles of space and time become interchanged in a sense. The radial direction toward the singularity becomes time-like, meaning it's unavoidable like the future. You can't stop falling toward the singularity any more than you can stop time from moving forward. Meanwhile, the direction of time becomes space-like. You could, in principle, move forward or backward in time, though this doesn't help you escape the singularity. These mind-bending properties of black hole interiors are firmly predicted by general relativity, yet they seem to conflict with quantum mechanics in profound ways. The conflict centers on information. Quantum mechanics holds that information is never truly destroyed. The quantum state of a system evolves deterministically, and in principle, you can always reverse the evolution and recover the initial state. But if you throw a book into a black hole, where does the information contained in that book go? According to classical general relativity, it falls into the singularity and is lost forever. This apparent destruction of information violates quantum mechanics, leading to what Stephen Hawking called the black hole information paradox. Hawking's own work in the 1970 seconds made the paradox more acute. He showed that black holes aren't completely black. They emit quantum radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation causes black holes to slowly evaporate. A stellar mass black hole would take vastly longer than the current age of the universe to evaporate, and a supermassive black hole like Sagittarius A times would take even longer, around 1090 years. But eventually, the black hole would vanish, and with it, seemingly, all the information that ever fell in. This paradox has driven decades of theoretical research. Recent work suggests that information might be preserved after all, encoded in subtle correlations in the Hawking radiation, or perhaps stored in a quantum structure at the event horizon. Some theories propose that the event horizon has fine structure, perhaps a firewall of intense radiation, perhaps a fuzzball of quantum strings, perhaps something else entirely. But these remain speculative ideas, awaiting a complete theory of quantum gravity to resolve. For Sagittarius A*, these quantum gravitational effects are far too subtle to observe with any foreseeable technology. The Hawking temperature of the black hole, the temperature of the radiation it emits, is about 10⁻14 Kelvin, far colder than the cosmic microwave background. The Hawking radiation is completely swamped by other sources of radiation and is impossible to detect. So while the event horizon of Sagittarius A times is a laboratory for testing general relativity, it's not a laboratory for testing quantum gravity, at least not yet. Chapter 15. The broader context. Black holes in the universe. Sagittarius A times doesn't exist in isolation. It's part of a vast population of black holes spread throughout the universe, ranging from stellar mass black holes formed in supernova explosions to the supermassive behemoths at the centers of galaxies, to possibly even larger ultramassive black holes in the most massive galaxies. Recent surveys have revealed just how common black holes are. The Milky Way alone likely contains 100 million stellar mass black holes, the remnants of massive stars that have lived and died over the galaxy's history. Most of these are isolated and invisible, detectable only if they happen to have a companion star from which they can accrete material. But when they do accrete, they reveal themselves as X-ray sources, binary star systems, where material streaming from a normal star onto a black hole heats up and emits intense X-rays. Beyond our galaxy, supermassive black holes appear to be universal features of large galaxies. Survey after survey has confirmed that essentially every galaxy with a substantial bulge, a concentration of stars at its center, harbors a supermassive black hole. The masses of these black holes range from millions to tens of billions of solar masses, with the mass correlated with properties of the host galaxy, as we discussed earlier. Some of these supermassive black holes are quiescent, like Sagittarius A*, quietly sitting at the centers of their galaxies, with little ongoing accretion. Others are ravenously feeding, accreting gas at prodigious rates and releasing enormous amounts of energy. These active galactic nuclei can outshine their entire host galaxies, visible across billions of light-years of space. The most luminous active galactic nuclei are called quasars, and they were much more common in the early universe than they are today, suggesting that supermassive black holes were more actively growing in the past. The LIGO and Virgo gravitational wave detectors have opened a new window on the black hole population. Since their first detection in 2015, these instruments have observed dozens of black hole mergers, binary black hole systems that spiral together and merge, releasing a final burst of gravitational waves. These observations have revealed that stellar mass black holes are more massive than previously thought, with many in the range of 20 to 40 solar masses, and some even heavier. There's also evidence for intermediate mass black holes filling the gap between stellar mass and supermassive black holes. Some of the gravitational wave detections involve black holes of 100 to a few hundred solar masses. X-ray observations have found candidates for intermediate mass black holes in dense star clusters. These might represent an intermediate stage in black hole growth, or could be a separate population with their own formation mechanism. At the very extreme, there are candidate ultramassive black holes exceeding 10 billion solar masses. The largest known black hole, TON 618, is estimated to contain 66 billion solar masses, more than 15,000 times more massive than Sagittarius A*. How such monsters form and grow remains an open question. They seem to require both an early start and sustained accretion over cosmic time, possibly in galaxies that have undergone multiple major mergers. The population of black holes tells us about stellar evolution, galaxy evolution, and the history of structure formation in the universe. The mass function of black holes, how many black holes exist at each mass range, reflects the initial mass function of stars, the physics of supernova explosions, and the merger history of galaxies. The spin distribution of black holes encodes information about how they formed and grew. Black holes that grow primarily through gas accretion should have high spins aligned with their accretion disks, while black holes that grow through mergers might have more random spin orientations. Black holes also play crucial roles in shaping the universe around them. We've mentioned AGN feedback, how energy from actively accreting supermassive black holes can heat gas and regulate star formation. This feedback appears to be crucial for explaining why the most massive galaxies stopped forming stars. Without black hole feedback in theoretical models, simulations produce galaxies that are too massive and too star-rich compared to observed galaxies. Stellar mass black holes in binary systems might be important sources of heavy elements. When a black hole accretes matter from a companion star, some of that matter is blown away in winds and jets. enriched with heavy elements forged in the hot accretion disk. Over time, this could contribute to the chemical evolution of galaxies, though the importance of this process compared to other sources of heavy elements is still being debated. There's even speculation that black holes might be connected to dark matter, the mysterious substance that makes up about 85% of the matter in the universe. Most physicists think dark matter consists of exotic subatomic particles, but an alternative idea is that it might be made up of primordial black holes. Black holes formed in the very early universe from quantum fluctuations. These would be stellar mass or smaller, permeating the universe and providing the extra gravity needed to explain galactic rotation curves and other observations. Current observations constrain but haven't ruled out primordial black holes as a dark matter candidate. Sagittarius A** as the nearest supermassive black hole and the one we can study in the greatest detail, serves as a touchstone for understanding this diverse population. Everything we learn about Sagittarius A times its mass, size, spin, accretion properties, and influence on its surroundings informs our understanding of black holes throughout the universe and across cosmic time. Chapter 16: Future Observations and Unanswered Questions. The first image of Sagittarius A times is a milestone, but it's far from the end of the story. Astronomers are already planning more observations and developing new technologies to study the black hole in even greater detail. These future observations promise to answer lingering questions and almost certainly raise new ones. One immediate goal is to improve the resolution and sensitivity of the Event Horizon Telescope. The 2017 observations used 8 telescopes, but more facilities are joining the network. The Greenland telescope has been added since 2017. The Kitt Peak 12-meter telescope in Arizona is being upgraded for EHT observations. The Africa Millimeter telescope is under construction in Namibia. Each additional telescope improves the coverage of the UV plane and increases the sensitivity of the array. There are also plans to extend the EHT into space. A space-based millimeter wave telescope orbiting Earth could provide baselines much longer than Earth's diameter, dramatically improving the angular resolution. Such a mission could potentially resolve the photon ring, the bright feature at the very edge of the shadow that we discussed earlier. Measuring the properties of the photon ring would provide even more stringent tests of general relativity. The EHT is also expanding to observe at multiple wavelengths simultaneously. The 2017 observations were at 1.3 millimeters. Adding observations at 0.8, 7 millimeters, 345 gigahertzes, provides complementary information. The shorter wavelength offers better resolution and less scattering, though atmospheric conditions are more challenging. Multi-wavelength observations can help disentangle the effects of scattering from the intrinsic structure of the emission region. Another major goal is to make movies, not just snapshots. The variability of Sagittarius A times on minute 2-hour timescales means that the structure of the bright ring is constantly changing. Hotspots in the accretion disk orbit around the black hole, appearing and disappearing. By tracking these motions, astronomers can directly measure the orbital motion of plasma near the event horizon, providing another test of general relativity and constraints on the black hole's spin. Creating movies requires observing Sagittarius A times continuously for many hours or even days, building up enough data to track how the structure evolves. The EHT team is developing new techniques for this, including ways to account for gaps in coverage as different telescopes rise and set at different times. Future campaigns will focus on obtaining longer, continuous coverage to enable movie reconstruction. Beyond the EHT, other telescopes at different wavelengths, provide complementary views of Sagittarius A asterisk. X-ray observatories like Chandra watch for flares, sudden brightenings that occur when magnetic reconnection events accelerate electrons to extremely high energies. These flares provide information about the magnetic field structure and plasma processes near the black hole. Infrared telescopes, including the upcoming extremely large telescope, a 39-meter optical infrared telescope under construction in Chile, will continue to track stars orbiting Sagittarius A asterisk, providing ever more precise measurements of the black hole's mass and potentially detecting new stars on even tighter orbits. Radio telescopes at longer wavelengths observe larger-scale structures. While these wavelengths can't resolve the shadow, they can trace outflows and jets extending light-years from the black hole, providing context for what's happening in the immediate vicinity of the event horizon. Coordinated multi-wavelength campaigns, with many telescopes observing Sagittarius A times simultaneously at wavelengths from radio through X-rays, can provide a complete picture of how the system behaves. There are also intriguing questions about what's happening very close to the event horizon that current technology can't yet address. Is there a relativistic jet being launched? The EHT observations show some hints of asymmetric structure that might represent a weak jet, but confirming this requires higher resolution. If a jet exists, what's launching it? Is it magnetic fields threading the event horizon, the Blandford-Znajek mechanism, or magnetic fields in the inner accretion disk, the Blandford-Payne mechanism? What is the black hole's spin? As we've discussed, this is still uncertain. The spin affects the size and shape of the shadow, the location of the ISCO, and the precession of stellar orbits. Better measurements of any of these could constrain the spin. The spin is important because it tells us about the black hole's history, how it grew, and what forces shaped its evolution. Is general relativity exactly correct? Or are there small deviations? Current measurements are consistent with general relativity, but there's still room for small modifications. More precise measurements of the shadow size and shape, the stellar orbital precession, and the behavior of hotspots in the accretion disk could potentially reveal deviations from Einstein's predictions. Such deviations would be revolutionary, pointing toward new physics. What about the environment around Sagittarius A asterisk? The galactic center is a unique place, the highest concentration of stars in the galaxy, with dozens of stars packed into each cubic light-year in the innermost regions. How do these stars affect the accretion flow onto the black hole? Stars have winds, streams of particles blown off their surfaces. These winds contribute gas to the environment around Sagittarius A asterisk. Some simulations suggest that winds from the densely packed stars in the galactic center might be the primary source of gas accreting onto the black hole. There's also the question of whether planets or other objects might orbit close to Sagittarius A asterisk. While the tidal forces and radiation environment make this region extremely hostile, it's not impossible that planets or asteroids could survive on orbits outside the immediate danger zone. Detecting such objects would be extraordinarily difficult, but not necessarily impossible with future technology. Looking further ahead, there are even more speculative possibilities. Could we someday send a probe to the galactic center? The distance 26,000 light-years makes this far beyond current technology, but it's fun to imagine what a probe close to Sagittarius A times might detect. Could we use precision timing of pulsars near the galactic center, if any exist in such an environment, to detect gravitational waves from Sagittarius A asterisk? The black hole might be accreting clumps of matter or interacting with other massive objects in ways that produce detectable gravitational wave signals. Could we even image other supermassive black holes with the same detail we've achieved for Sagittarius A times and M87*? Most supermassive black holes are much farther away and would require even better angular resolution, but some, like the black hole at the center of the Andromeda Galaxy, our nearest large galactic neighbor, 2.5 million light-years away, or Centaurus A, a nearby active galaxy, might be accessible to future instruments. Each answered question raises new ones. That's the beauty of science. Each discovery opens new avenues of inquiry. Each observation reveals unexpected phenomena. Each test of theory suggests new tests. Sagittarius A times has been studied for 50 years, imaged in 2022, and yet we've barely scratched the surface of what it can teach us. Chapter 17. What Sagittarius A times teaches us about the universe. Let's step back and consider the broader significance of what we've learned about Sagittarius A*. This isn't just about one black hole in one galaxy. The insights gained from studying Sagittarius A times reverberate through multiple fields of physics and astronomy, touching on fundamental questions about the nature of space, time, matter, and the cosmos itself. First and foremost, Sagittarius A times provides the strongest evidence that black holes, objects so strange that even Einstein doubted their existence, are not just theoretical curiosities, but real, physical objects. The combination of stellar orbit observations showing a massive invisible object and the EHT image showing a shadow with precisely the expected size and shape leaves essentially no doubt. Black holes exist, and we can see their signatures directly. This confirmation matters because black holes represent the ultimate test of our theories of gravity. Newton's gravity works beautifully for everyday situations, calculating planetary orbits, designing bridges, landing spacecraft on Mars, but it breaks down in strong gravitational fields. Einstein's general relativity extends our understanding to these extreme regimes, and the observations of Sagittarius A times confirm that Einstein's century-old theory still works even at the edge of a black hole event horizon. But general relativity's success at Sagittarius A times also highlights its limitations. The theory predicts singularities, points where density and curvature become infinite. Yet, infinity has no place in physics. It's a sign that the theory has reached its limits. We need quantum gravity to go further, and observations of black holes help guide the search for this deeper theory. Every measurement of a black hole, property, mass, spin, shadow size, is a data point that any future theory of quantum gravity must explain. Sagittarius A times also illustrates the intimate connection between galaxies and their central black holes. The fact that supermassive black holes are universal, that their masses correlate with galaxy properties, and that their activity influences star formation, suggests that we can't understand galaxies without understanding black holes, and vice versa. This coevolution is a major theme in modern astrophysics, affecting our understanding of how the universe evolved from the simple conditions shortly after the Big Bang to the rich cosmic ecosystem we see today. The techniques developed to image Sagittarius A times very long, baseline interferometry, sophisticated imaging algorithms, massive data processing, have applications far beyond black hole astronomy. VLBI is used to study everything from pulsars to distant quasars to jets from stellar mass black holes. The data processing techniques developed for the EHT have influenced fields from medical imaging to computer vision. The international collaboration required to coordinate observations across the globe provides a model for large-scale scientific cooperation. Sagittarius A times also serves as a reminder of humanity's place in the cosmos. We live in a galaxy of hundreds of billions of stars, orbiting around a supermassive black hole 26,000 light-years from our solar system. We're not at the center, we're about halfway out in one of the spiral arms, orbiting the galactic center once every 230 million years. In the 4.6 billion years since Earth formed, our solar system has orbited the galaxy about 20 times. The stars we see in the night sky are our local neighbors, typically within a few hundred light-years. Sagittarius A*, despite being our galaxy's most massive single object, is so distant that it has essentially no direct influence on our solar system, yet we can observe it, measure it, image it. The photons captured by the Event Horizon Telescope left the vicinity of Sagittarius A times 26,000 years ago, when humans on Earth were still hunter-gatherers in the Stone Age. Those photons traveled across the galaxy, passing through clouds of gas and dust, bending around stars, gradually making their way to Earth, where they happened to arrive in April 2017 and were captured by our telescopes. By analyzing these ancient photons, we can reconstruct what was happening near the event horizon of a supermassive black hole in the distant past. This ability to observe, understand, and measure objects so distant and extreme represents one of humanity's greatest achievements. We're using tools built from rocks and metals, powered by electricity generated from sunlight or fossil fuels, or nuclear reactions, controlled by computers built from refined sand, to peer into the deepest mysteries of nature. We're using mathematics, abstract patterns of logic, to predict what reality should look like, then checking whether reality agrees. And amazingly, it does. The story of Sagittarius A times is also a story about scientific perseverance and collaboration. From Jansky's discovery in the 1,930 seconds to the EHT image in 2022 spans nearly a century. Thousands of scientists contributed building telescopes, developing theories, taking observations, analyzing data, checking results. Some, like Jansky and Schwarzschild, never knew the full impact of their work. Others, like Genzel and Ghez, devoted entire careers to studying this single object. The Nobel Prize recognizing their work acknowledges not just individual achievement, but the collective enterprise of science itself. Chapter 18. Sagittarius A times in culture and philosophy. Beyond its scientific importance, Sagittarius A times has captured public imagination and raised profound philosophical questions. The idea of a black hole, a region where space and time behave so strangely that our intuitions fail, challenges our understanding of reality itself. Black holes have featured prominently in science fiction for decades, often portrayed as cosmic whirlpools that suck in everything nearby, or as portals to other universes or different times. While the reality is somewhat less dramatic, Sagittarius A times isn't going to suddenly gobble up Earth. We're far too distant to be in any danger. The truth is, in some ways, even stranger than fiction. A real event horizon, where time stops from an outside perspective but continues normally for an infalling observer, where the future becomes inevitable like a direction in space. These properties challenge our basic notions of cause and effect, of before and after, of here and there. The image of Sagittarius A*, released in 2022, became iconic almost instantly. That bright ring surrounding the dark center appeared in news articles worldwide, was shared millions of times on social media, and inspired countless artworks, visualizations, and creative interpretations. For many people, it was their first glimpse of a black hole, not an artist's illustration or a computer simulation, but an actual photograph, or as close to a photograph as radio interferometry can produce, of one of the universe's most exotic objects. The image resonates emotionally as well as intellectually. There's something deeply moving about seeing the unseeable, about knowing that dark circle represents the edge of forever, a boundary beyond which no information returns. It's a visualization of ultimate mystery we can see up to the edge, but the interior remains forever hidden, not just practically, but in principle. Even if you could survive the journey to the event horizon and cross it, you could never report back what you found. This has philosophical implications that have been debated for centuries, going back to the earliest musings about dark stars. If information is truly destroyed in black holes, though as we discussed, quantum mechanics suggests it might not be, does that mean the universe is not deterministic? If you can't predict what happens to matter that falls into a black hole, does that violate the principle that the same initial conditions always produce the same outcome? Black holes also raise questions about the nature of space and time. We experience space as three-dimensional and time as a separate, one-directional flow. But general relativity unifies these into four-dimensional space-time, where the distinction between space and time is somewhat arbitrary. What one observer sees as space, another observer, moving at a different velocity, sees as a mixture of space and time. Near a black hole, this becomes even more extreme, with space and time playing roles that our evolved intuitions never prepared us for. There's also the question of whether black holes are truly permanent. Hawking radiation suggests they're not, that they slowly evaporate over unimaginably long timescales. A black hole is thus not eternal, but metastable, doomed to eventually vanish in a final burst of radiation. For Sagittarius A*, this process would take so long that it's meaningless on human timescales. But it's philosophically significant. Nothing in the universe is permanent. Even black holes, the most permanent seeming objects imaginable, eventually decay. In some spiritual and philosophical traditions, black holes have become metaphors for various concepts: the void, the unknown, the unconscious, death and rebirth. While these metaphorical uses often diverge from the physics, they speak to the powerful symbolism of a black hole. It represents ultimate extremes, the densest possible concentration of matter, the strongest possible gravitational field, the most thoroughly isolated interior region possible. It's an object that exists at the boundary of our understanding, challenging us to expand our knowledge and accept the limits of what we can know. The study of Sagittarius A times also exemplifies certain values: curiosity, persistence, collaboration, and the belief that nature is comprehensible. Why spend decades tracking stars around an invisible object? Why build a telescope network spanning the Earth? Why develop complex mathematics to predict what a black hole shadow should look like? Because we want to understand. Because the universe is there, strange and beautiful, and governed by rules we can discover through observation and reason. This drive to understand, to take a phenomenon that seems mysterious or impossible, and gradually, through patient effort, figure out what it is and how it works, is one of humanity's defining characteristics. Sagittarius A times represents this drive in its purest form. We can't go there, can't touch it, can barely see it, but we can understand it, can measure its properties, can test our theories against reality, and find that they work. This is the essence of science, and Sagittarius A times is one of its greatest triumphs. Chapter 19. The Technical Achievement. Let's appreciate just how remarkable the technical achievement of imaging Sagittarius A times really is. We've touched on many aspects of this throughout, but it's worth gathering them together to understand the full scope of what was accomplished. Consider the scale of the angular resolution required, 20 micro-arcseconds. This is equivalent to seeing a donut on the moon from Earth, or reading a newspaper in Los Angeles from New York, or resolving a golf ball in Frankfurt from New York, or distinguishing two fireflies separated by 10 centimeters in Tokyo from the Empire State Building in New York. We're pushing the limits of what's possible with current technology, and in some ways, exceeding what many thought possible. The telescopes themselves represent cutting-edge technology. The receivers that detect the millimeter wavelength radio signals use superconducting electronics cooled to near absolute zero. At these temperatures, quantum effects become important, and the careful design is required to minimize noise and maximize sensitivity. The telescopes themselves represent cutting-edge technology. The receivers that detect the millimeter wavelength radio signals use superconducting electronics cooled to near absolute zero. At these temperatures, quantum effects become important, and the careful design is required to minimize noise and maximize sensitivity. The analog signals from these receivers are digitized at rates of billions of samples per second, capturing the full complexity of the incoming radio waves. The atomic clocks ensuring time synchronization are marvels in their own right. A hydrogen maser atomic clock uses the quantum transition of hydrogen atoms to keep time with extraordinary precision. These clocks lose only about 1 second every 100 million years. For the EHT observations, even this isn't quite good enough. The clocks need to be continuously synchronized using GPS signals and carefully monitored to ensure any drift is detected and corrected. The data recording system had to handle unprecedented data rates. 64 gigabits per second of data, sustained for hours, adds up quickly. Special high-performance recording systems were developed specifically for VLBI applications. Each telescope site required multiple high-capacity hard drive modules that could reliably record data at extreme rates without dropping samples. The drives had to work in harsh environments, thin air at high altitude, extreme cold in Antarctica, potential power fluctuations at remote sites. The data correlation process represents a massive computational challenge. Correlating signals from 8 telescopes requires comparing every possible pair of telescopes, accounting for geometric delays as the signal reaches different sites at slightly different times, correcting for Earth's rotation and atmospheric effects, and numerous other factors. The correlation software is highly optimized, taking advantage of specialized computer architectures and parallel processing to complete the calculations in reasonable timeframes. The imaging algorithms are perhaps the most sophisticated part of the entire pipeline. Given the sparse sampling of the UV plane, we only observe certain spatial frequencies. Not all of them, infinitely many possible images could match the data. The challenge is to find the right image, or at least understand the range of possible images consistent with observations. This requires combining the data with additional information assumptions about what images are physically reasonable, statistical methods for dealing with noise and uncertainty, and ways to avoid artifacts introduced by the imaging process itself. The EHT team developed multiple independent imaging pipelines to tackle this problem. One approach, called CLIAN, is traditional in radio astronomy and works by iteratively identifying and subtracting point sources from the data. Another approach uses maximum entropy methods, finding the image that best matches the data while having the maximum possible entropy, minimum structure, consistent with that match. A third approach, called regularized maximum likelihood, uses various regularization terms to prefer images with certain desirable properties, smoothness, compactness, or edge preservation. Each imaging method has parameters that need to be set: regularization weights, stopping criteria, starting guesses. To ensure the results weren't biased by arbitrary choices, the teams working on different imaging pipelines were kept separate until all had produced their images. Only then were results compared. The remarkable agreement among different methods gave confidence that the ring-like structure seen in the images was real, not an artifact of any particular imaging approach. Testing the algorithms required generating synthetic datasets, simulated observations of black holes with known properties, processed through realistic models of the telescope array and observation process. If the imaging algorithms could successfully recover the known input from these synthetic observations, that gave confidence they could work with real data. Hundreds of simulated datasets were created and processed, testing the algorithms under various conditions. The team also had to account for systematic effects that could bias the results. Atmospheric turbulence causes rapid fluctuations in the signal, requiring careful calibration to correct for these effects without removing real structure in the source. Instrumental effects, slightly different gain or phase responses in different telescopes, need to be measured and corrected. The interstellar scattering we mentioned earlier had to be modeled and accounted for. All of this work happened over a 5-year period, from the April 2017 observations to the May 2022 image release. Hundreds of scientists and engineers contributed, telescope operators keeping the instruments running during the observations, experts in data correlation ensuring all the data could be properly combined, theorists running simulations to interpret the results, and many others. The Event Horizon Telescope collaboration includes over 300 researchers from dozens of institutions across 6 continents. The project required not just technical expertise, but also diplomacy and coordination. Telescope time is precious. Every hour spent observing Sagittarius A times is an hour not available for other scientific projects. Coordinating 8 major observatories to observe the same target at the same time required years of planning and negotiation. Weather could derail observations at any site, requiring backup plans and flexible scheduling. Data had to be physically shipped from remote sites, requiring careful handling and secure transport of irreplaceable hard drives. Funding came from agencies in multiple countries: the US National Science Foundation, the European Research Council, funding agencies in Japan, South Korea, Taiwan, and many others. This international collaboration represents not just scientific achievement, but also human cooperation across borders and cultures, united by the common goal of understanding the universe. The technical achievement of imaging Sagittarius A times will likely stand as one of the landmark accomplishments of 21st century astronomy, comparable to Hubble's discovery of the expansion of the universe, the cosmic microwave background detection that confirmed the Big Bang theory, or the first detection of gravitational waves. It required pushing multiple technologies to their limits simultaneously and combining expertise from diverse fields: radio, astronomy, general relativity, plasma physics, computer science, and more. Chapter 20. The View from Here. Our Cosmic Perspective. As we near the end of our journey, it's worth reflecting on what it means that we, a species of primates, on a small rocky planet orbiting an ordinary star in the suburbs of a typical spiral galaxy, can measure the size of a supermassive black hole at the galaxy's center. Our Sun is one star among 200 to 400 billion stars in the Milky Way. It's located about 26,000 light-years from the galactic center, roughly halfway out toward the edge of the visible disk. We orbit the center on a roughly circular path, taking about 230 million years to complete one orbit. This means that in the entire history of our solar system, 4.6 billion years, we've completed only about 20 orbits around the galaxy. The stars near us are similar to the Sun in many ways. They're relatively old, enriched with heavy elements from earlier generations of stars, located in the disk where gas clouds continue to form new stars. But the galactic center is a different environment entirely. The density of stars is millions of times higher than in our neighborhood. Stars there experience close encounters with other stars. Some are torn apart by tidal forces from Sagittarius A times or from close passes to other stars. The radiation environment is harsh, with X-rays and high-energy particles more common than in our quiet corner of the galaxy. If our solar system were located in the galactic center, the night sky would be dramatically different. Instead of a few thousand stars visible to the naked eye, there might be millions, making the sky bright enough to read by, even at night. The region around Sagittarius A times would glow with X-rays and gamma rays from the hot plasma in the accretion disk, though these would be invisible to human eyes. If our solar system were located in the galactic center, the night sky would be dramatically different. Instead of a few thousand stars visible to the naked eye, there might be millions, making the sky bright enough to read by even at night. The region around Sagittarius A times would glow with X-rays and gamma rays from the hot plasma in the accretion disk, though these would be invisible to human eyes. Every few weeks or months, a bright flare might erupt as magnetic reconnection events release stored energy. Of course, life as we know it probably couldn't exist so close to the galactic center. The radiation environment would be too harsh, sterilizing planetary surfaces. Close encounters between stars would perturb planetary orbits, possibly ejecting planets from their solar systems entirely. And the probability of a nearby supernova or gamma ray burst would be much higher, potentially devastating any life that did manage to emerge. So we're fortunate to be where we are, far enough from the galactic center to enjoy relative safety and stability, but close enough that we're bound to the galaxy and not adrift in intergalactic space. And from this safe distance, we can observe the galactic center, study Sagittarius A*, and learn about the extreme physics that governs the innermost regions of our galaxy. This ability to observe and understand objects we can never visit is one of the most remarkable aspects of science. We'll never send a probe to Sagittarius A times. The travel time would be hundreds of millions of years, even at the speed of light, and we have no technology even approaching such speeds. Yet we can measure its properties with precision, test theories of gravity against its behavior, and understand how it shapes the galaxy around it. This is possible because the universe is comprehensible. The same physical laws that govern falling objects on Earth also govern the motion of planets around the Sun, stars around the galactic center, and even light near a black hole event horizon. By discovering these laws through local experiments and observations, we can apply them to the farthest reaches of the universe. The conservation of energy, discovered in laboratory experiments on Earth, applies to accretion disks around black holes. The electromagnetic radiation produced by accelerating charges in our labs is the same phenomenon producing light from plasma near Sagittarius A*. This universality of physical law is not logically necessary. We can imagine a universe where different regions operated by different rules, where the laws of physics changed with time or location. But our universe isn't like that. The same atoms that make up Earth are found in stars across the galaxy, and in galaxies billions of light years away. The same forces: gravity, electromagnetism, the strong and weak nuclear forces operate everywhere we can observe. This uniformity makes astronomy possible. It allows us to interpret the light from distant objects and infer what they're made of, how they're moving, and what forces shape them. The Sagittarius A times observations exemplify another crucial aspect of modern science: the combination of theory and observation working together. Theory in this case, general relativity and plasma physics, tells us what to expect. Observations test whether reality matches expectations. When they agree, as they do for Sagittarius A*, our confidence in the theory increases. When they disagree, we've learned something even more valuable: that our understanding is incomplete and needs revision. This interplay between theory and observation has driven scientific progress for centuries. Newton's theory of gravity predicted planetary motions that matched observations extremely well, but tiny discrepancies in Mercury's orbit hinted at something deeper. Einstein's general relativity explained these discrepancies and predicted new phenomena: gravitational lensing, black holes, gravitational waves that were subsequently observed. Each observation that confirms a theoretical prediction strengthens our confidence. Each observation that contradicts theory drives us to better understanding. For Sagittarius A*, theory made clear predictions. A black hole of 4.3 million solar masses should cast a shadow of approximately 52 micro-arcseconds. Observation confirmed this prediction within measurement uncertainties. This is how science works, not through proof in the mathematical sense, but through the accumulation of evidence, the testing of predictions, and the gradual refinement of our understanding to match reality ever more closely. Chapter 21: Connections Across Cosmic Scales. The physics governing Sagittarius A times connects to phenomena across a vast range of scales, from the quantum realm to the entire observable universe. Understanding these connections reveals how deeply interconnected different areas of physics are. At the smallest scales, quantum mechanics governs the behavior of individual particles. The electrons spiraling in magnetic fields around Sagittarius A*, producing the synchrotron radiation we observe, are quantum particles with quantized energy levels and wave-like properties. The photons carrying energy away from the black hole are quantum particles of light, each with a specific energy determined by Planck's constant times its frequency. Hawking radiation, which we discussed earlier, is a purely quantum phenomenon. It arises from quantum fluctuations near the event horizon, virtual particle-antiparticle pairs that normally appear and annihilate almost instantly. Near the horizon, one particle can fall in while the other escapes, resulting in a net emission of radiation. This process connects quantum mechanics, the physics of the very small, with general relativity, the physics of the very large. The interior of a black hole, where the singularity resides, requires a theory of quantum gravity that doesn't yet exist. String theory, one candidate for such a theory, proposes that fundamental particles are not points but tiny vibrating strings. The different vibrational modes of these strings correspond to different particles. In this framework, black holes might have microstructure, a vast number of quantum states corresponding to different configurations of strings. The entropy of a black hole, its disorder or information content, would be related to the number of these quantum states. Loop quantum gravity, another approach to quantum gravity, proposes that space itself is quantized. At the smallest scales, there's a minimum possible length, called the Planck, length about 10, -35 meters, and space-time is built from discrete quantum units. In this picture, the singularity might be replaced by a quantum bounce, where infalling matter reaches a maximum density but doesn't become truly infinite. These quantum gravitational ideas remain speculative, but black holes like Sagittarius A times provide the most promising arena for eventually testing them. Any observable predictions of quantum gravity theories would be most dramatic near black hole event horizons, where quantum effects and strong gravitational fields coexist. Moving up in scale, atomic and nuclear physics play crucial roles in the environment around Sagittarius A*. The plasma in the accretion disk is fully ionized atoms, stripped of their electrons due to the extreme temperatures. The behavior of this plasma depends on electromagnetic interactions between charged particles. Magnetic fields, generated by currents in the plasma, shape the flow of material and launch outflows. All of this is governed by Maxwell's equations of electromagnetism, formulated in the 19th century but still perfectly valid in these extreme conditions. Stars orbiting Sagittarius A times are powered by nuclear fusion in their cores, the same process that powers our Sunday. Light nuclei fuse to form heavier nuclei, converting mass to energy according to Einstein's E equals mc². The heavy elements that make up planets and ultimately life, carbon, oxygen, nitrogen, iron, were forged in earlier generations of stars and scattered through space when those stars exploded as supernovae. The stars we observe near Sagittarius A times contain these heavy elements, indicating they formed from gas enriched by previous stellar generations. At galactic scales, Sagittarius A times influences the structure and evolution of the Milky Way. Though it contains only about 0.01% of the galaxy's total mass, its central location and the energy released during active periods can affect the distribution of gas and the rate of star formation in the central regions. The orbits of stars throughout the galaxy are determined by the combined gravitational field of all the matter, stars, gas, dark matter, and the supermassive black hole at the center. The Milky Way itself is part of the local group of galaxies, which includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. The local group is embedded in the larger Laniakea supercluster, a structure containing about 100,000 galaxies spanning 500 million light-years. All of these structures are shaped by gravity operating over vast timescales. At the largest scales, the expansion of the universe itself comes into play. The Milky Way and Andromeda are gravitationally bound and will eventually merge in about 4.5 billion years. When they do, their central supermassive black holes, Sagittarius A times, and Andromeda's black hole, which is perhaps 10 times more massive, will eventually sink to the center of the merged galaxy and themselves merge, creating a single black hole containing tens of millions of solar masses. But most galaxies are not bound to us. They're being carried away by the expansion of space itself, described by the Hubble-Lemaitre law, first discovered in the 1920 seconds. This expansion is not galaxies moving through space, but rather space itself expanding, carrying galaxies along with it. The expansion is accelerating, driven by dark energy, a mysterious component that makes up about 68% of the universe's total energy density. We don't know what dark energy is, though observations suggest it behaves like a cosmological constant, a uniform energy density permeating all of space. This is one of the deepest mysteries in physics, and understanding it requires combining knowledge from quantum field theory, general relativity, and cosmology. So the story of Sagittarius A times connects to nearly every domain of physics: quantum mechanics at the smallest scales, atomic and nuclear physics in stars, electromagnetic theory in plasma dynamics, general relativity in curved spacetime, astrophysics at galactic scales, and cosmology at the largest scales. Each of these domains informs our understanding of the others, and black holes like Sagittarius A times sit at the intersection, combining extreme conditions that test multiple areas of physics simultaneously. Chapter 22. The human story behind the science. Behind every scientific discovery are human stories of curiosity, dedication, frustration, breakthrough, and the joy of understanding. The story of Sagittarius A times involves thousands of individuals over nearly a century, each contributing a piece to the puzzle. Carl Jansky, who first detected radio emission from the galactic center in 1932, worked at Bell Labs, not as an astronomer, but as a radio engineer trying to reduce static in telephone communications. His discovery was essentially an accident. He wasn't looking for astronomical radio sources because no one knew they existed. After announcing his discovery, Jansky wanted to pursue radio astronomy, but Bell Labs wasn't interested in funding such research, and Jansky spent the rest of his career on other projects. He died in 1950 at age 44, never knowing that his discovery would launch an entire field. The fundamental unit of radio flux density, the Jansky, is named in his honor. Grote Reber, inspired by Jansky's work, built the first radio telescope specifically for astronomy in his backyard in Illinois in 1937. He conducted the first radio sky surveys at his own expense, working as an engineer by day and observing the sky at night. His pioneering work helped establish radio astronomy as a legitimate scientific field. Karl Schwarzschild, who found the first solution to Einstein's field equations describing a black hole, did so while serving on the Russian front in World War I. Despite suffering from a painful autoimmune disease, probably pemphigus, he continued his scientific work, sending papers back to Einstein in Berlin. He died in May 1916 at age 42, just months after his black hole solution was published. He couldn't have imagined that objects described by his mathematics really existed in nature. Subramanian Chandrasekhar calculated in 1930, while a student traveling by ship from India to England, that there's a maximum mass for white dwarf stars, about 1.4 solar masses. Above this mass, now called the Chandrasekhar limit, a star's core must collapse to something denser. This was one of the first hints that black holes might be necessary consequences of stellar evolution. Chandrasekhar faced significant skepticism from established astronomers, but his work was eventually vindicated, and he received the Nobel Prize in 1983. John Wheeler, who coined the term black hole in 1967, was a giant of 20th century physics. He contributed to nuclear physics, worked on the atomic bomb during World War II, mentored numerous future Nobel laureates including Richard Feynman and Kip Thorne, and played a crucial role in establishing black holes as respectable objects of study. Before Wheeler's advocacy, many physicists dismissed black holes as mathematical curiosities with no physical reality. The teams, led by Reinhard Genzel and Andrea Ghez, began their observations of the galactic center in the 1990 seconds and continued for over 2 decades before receiving the Nobel Prize in 2020. This long-term commitment represents a particular kind of scientific courage, choosing to devote a career to a project with no guarantee of success, requiring consistent effort year after year with incremental progress. Ghez, in particular, had to overcome additional obstacles as a woman in physics, a field that has historically been unwelcoming to women. Her success and recognition have inspired a new generation of women astronomers and physicists. The Event Horizon Telescope collaboration includes people from diverse backgrounds, cultures, and career stages. Shep Doleman, the project director, spent years advocating for the project and raising funds before the first observations. Katie Booman, who developed some of the key imaging algorithms as a graduate student, became famous when the M87 Times image was released in 2019, though she emphasized that the success was due to the entire team's efforts. Dozens of graduate students and postdocs spent years working on various aspects of the project, often on specific technical problems that may seem narrow but were crucial to the overall success. The telescope operators and support staff who keep the instruments running often receive less public recognition but are equally essential. Running a millimeter wave telescope at 5,000 meters altitude in the Chilean desert or at the South Pole in Antarctica is physically demanding work. The data analysts who process petabytes of data, the software engineers who write the correlation and imaging code, the administrators who manage the collaboration and funding, all contribute to the final result. There's also the story of the ideas that didn't work, the dead ends and failures that are an inevitable part of research. Not every observation yields useful data. Weather can interfere, instruments can malfunction, and sometimes the data quality just isn't good enough. Not every imaging algorithm works. Some were tried, failed to produce reliable results, and were abandoned. Not every theoretical model matches observations. Many predicted properties of black holes don't match what we see, forcing theorists to revise their understanding. This human dimension of science, the effort, creativity, collaboration, and yes, occasional conflict and competition, is often hidden behind the polished final results, published in journals or announced at press conferences. But it's an essential part of the story. Science is done by people, with all the strengths and limitations that entails. Chapter 23. What we still don't know. Despite the remarkable progress in understanding Sagittarius A*, there remain numerous open questions and mysteries. Acknowledging what we don't know is just as important as understanding what we do know. The exact spin of Sagittarius A times remains uncertain. While observations suggest it's rotating, the precise spin parameter could be anywhere from about 0.4 to 0.9, where 1 represents maximum spin. This uncertainty matters because spin affects numerous observable properties. Better measurements of the shadow shape, stellar orbital precession, or jet properties could narrow this range, but current data don't yet allow a definitive determination. The nature of the accretion flow onto the black hole is still debated. Is it a traditional thin accretion disk, like a smaller version of the disk around a young star? Or is it an advection-dominated flow, where energy is advected inward with the accreting material rather than being radiated away. Or perhaps it's a combination, with different flow geometries at different radii. The low luminosity of Sagittarius A times suggests an inefficient accretion process, but the details remain unclear. The magnetic field structure near the event horizon is poorly constrained. Magnetic fields clearly play a crucial role. They likely launch the weak outflows observed from Sagittarius A times and might extract energy from the black hole's rotation through the Blandford-Zeenajek mechanism. But measuring field strengths and geometries requires techniques like polarimetry, measuring the polarization of light, and current data don't yet provide a complete picture. Whether Sagittarius A times has a jet is still uncertain. M87 times has a spectacular jet visible across thousands of light years. Sagittarius A times shows some asymmetric structure that might indicate a weak jet, but it's not clearly resolved. If a jet exists, why is it so much weaker than M87*'s jet? Is it related to the low accretion rate, the black hole's spin, or some other factor? The variability of Sagittarius A times on minute-to-hour timescales is observed but not fully understood. What physical processes create these rapid fluctuations? Are they hot spots orbiting near the innermost stable circular orbit, magnetic reconnection events, some other phenomenon? Movies from future EHT observations might help answer this, but detailed models connecting observations to underlying physics are still being developed. The history of Sagittarius A*'s growth remains mysterious. When did it form? How much of its mass came from gas accretion versus mergers with other black holes? Was there a period of rapid growth, or has it grown steadily over cosmic time? Clues might come from understanding the star formation history in the galactic center and from observations of supermassive black holes at different redshifts. Looking back in cosmic time, the dark matter distribution in the galactic center is uncertain. Dark matter halos are predicted to form dense cusps at galaxy centers, and such a cusp might affect stellar orbits or even the accretion flow onto Sagittarius A**. But observational evidence for or against such a cusp is limited. If dark matter particles occasionally annihilate near the black hole, they might produce detectable gamma rays or other signatures, but searches so far have found no clear signal. There might be intermediate mass black holes of thousands to tens of thousands of solar masses orbiting in the galactic center region. These could be remnants of globular clusters that were tidally disrupted while orbiting near Sagittarius A**. If they exist, they would affect the orbits of nearby stars and might occasionally get close enough to Sagittarius A times to produce observable effects. But finding them is challenging because they don't emit much light on their own. The ultimate fate of Sagittarius A times is predictable in broad strokes, but uncertain in detail. In about 4.5 billion years, the Milky Way and Andromeda galaxies will merge. The two central black holes will eventually sink to the center of the merged galaxy and form a binary system. This binary will emit gravitational waves, gradually losing energy until the black holes merge. But the precise timeline depends on details of the merger process that are hard to predict. Looking much further ahead, in the unimaginably distant future, Sagittarius A times will slowly evaporate through Hawking radiation. The timescale for this is about 90 years, a 1 followed by 90 zeros. For comparison, the current age of the universe is less than 11 years. So black hole evaporation is so slow as to be effectively irrelevant on any but the most extreme cosmological timescales. By the time Sagittarius A times evaporates, the universe will be a vastly different place. Stars will have long since burned out, galaxies will have evaporated or merged, and most matter will have decayed or been locked up in black holes. These open questions ensure that research on Sagittarius A times will continue for decades. Each answered question typically raises new questions, and mysteries resolved at one level reveal new mysteries at deeper levels. This is the nature of scientific inquiry, an endless frontier where each new understanding opens vistas of further questions. Chapter 24: The Legacy and Future. The study of Sagittarius A times has already secured a place in the history of science, but its story is far from over. The techniques, technologies, and insights developed through this work will influence astronomy and physics for generations. The Event Horizon Telescope represents a new paradigm for astronomy. Global collaboration using existing facilities in new ways rather than building a single massive instrument. This approach has advantages. It's more affordable, it leverages existing investments in infrastructure, and it benefits from diverse expertise spread across many institutions. Future projects might adopt similar models, creating virtual instruments from networks of telescopes for different purposes. The imaging algorithms developed for the EHT have applications beyond astronomy. The problem of reconstructing an image from incomplete or noisy data arises in medical imaging, CT scans, MRI, geophysical exploration, microscopy, and many other fields. Techniques developed for black hole imaging have already influenced these other domains, and future developments will likely flow in both directions. The EHT has also demonstrated the value of multi-messenger astronomy, using different types of observations to study the same object. Radio observations from the EHT, combined with infrared observations of stellar orbits and X-ray observations of flares, provide a complete picture that no single type of observation could achieve. Future facilities will increasingly adopt this multi-messenger approach, coordinating observations across wavelengths and even including gravitational waves and neutrinos. Educational impacts are significant. The iconic image of Sagittarius A times appears in textbooks and classrooms worldwide, inspiring students to study physics and astronomy. The technical challenges of the project provide excellent examples of how diverse areas of knowledge, mathematics, physics, engineering, computer science, come together to solve problems. The international collaboration demonstrates how science transcends political boundaries. Public engagement with science benefits from dramatic results like black hole images. These grab attention and spark curiosity, providing opportunities to explain not just the specific result, but the broader scientific process. How do we know what we know? Why should we trust scientific results? What's the difference between scientific theories and wild speculation? The Sagittarius A times story provides a case study for addressing these questions. Looking ahead, several specific developments seem likely. First, the EHT will continue to improve. Adding more telescopes increases resolution and sensitivity. Observing at multiple frequencies simultaneously provides more complete information. Space-based telescopes would dramatically improve baselines and image quality. Within the next decade or two, we might have movies of Sagittarius A times, showing the dynamics of the accretion flow in detail. Second, other black holes will be imaged. Sagittarius A times and M87 times are the first, but they won't be the last. Several other supermassive black holes are potential targets, the the black hole in Centaurus A, in NGC 1052, in NGC 3115, possibly even Andromeda's central black hole. Each new image will teach us something about the diversity of black holes and their environments. Third, gravitational wave astronomy will detect supermassive black hole mergers. Current detectors like LIGO see stellar mass black hole mergers. Future space-based detectors like LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s, will detect gravitational waves from mergers of supermassive black holes in distant galaxies. This will provide information about black hole populations across cosmic history. Fourth, detailed studies of stellar orbits around Sagittarius A times will continue. As more stars complete full orbits, measurements of the black hole's mass and position will improve. Precession effects will be measured more precisely, potentially determining the black hole's spin. If we're very lucky, a star might pass even closer to the black hole than S2, providing even more extreme tests of general relativity. Fifth, theoretical understanding will deepen. Better simulations incorporating more realistic physics, general relativistic magnetohydrodynamics with sophisticated plasma physics, detailed radiative transfer, multiple scales from the event horizon to the outer accretion flow will help interpret observations. As observations become more detailed, they'll constrain theories more tightly, driving progress in understanding accretion physics, jet launching, and the interaction between black holes and their environments. Sixth, unexpected discoveries are likely. History teaches that whenever we develop new observational capabilities, we discover things we didn't predict. Pulsars, quasars, gamma-ray bursts, gravitational waves, all were surprises. As black hole observations become more routine and detailed, we'll likely find phenomena that don't fit current theories, forcing us to expand our understanding. The legacy of Sagittarius A times research will extend beyond the specific scientific results. It demonstrates what human ingenuity can achieve when curiosity drives us to understand nature at its most extreme. It shows the power of international collaboration and long-term commitment. It exemplifies the interplay between theory and observation that drives scientific progress. And it reminds us that the universe still holds mysteries waiting to be revealed to those patient and clever enough to seek them out. Chapter 25. A Journey's End and a Beginning. We've traveled far in this exploration of Sagittarius A times, from its discovery as a mysterious radio source in the 1930 seconds, through decades of observations that revealed its nature as a supermassive black hole, culminating in the first direct image of its shadow in 2022. Along the way, we've explored black hole physics, general relativity, plasma dynamics, observational techniques, and the human stories behind the science. What have we learned? We now know with certainty that Sagittarius A times is a supermassive black hole containing 4.3 million solar masses, located 26,000 light-years from Earth at the center of our galaxy. Its event horizon has a diameter of about 25 million kilometers, and its shadow, as observed by the Event Horizon Telescope, spans about 52 micro-arc-seconds on the sky, equivalent to 52 million kilometers at the distance of the galactic center. This measurement is far more than just a number. It confirms decades of theoretical predictions about how black holes should appear. It validates Einstein's general theory of relativity in one of the most extreme gravitational environments in the universe. It demonstrates that event horizons, regions of space-time from which nothing can escape, really exist. And it provides a foundation for understanding supermassive black holes throughout the universe. But beyond the specific numbers and confirmations, the Sagittarius A times story teaches broader lessons. It shows that the universe is comprehensible, that even objects as exotic as black holes follow physical laws we can discover and understand. It demonstrates the power of patient observation combined with sophisticated theory. It exemplifies how technology developed for one purpose, radio astronomy, for studying terrestrial radio interference, can open entirely new windows on the universe. The story also highlights the importance of asking basic questions. How big is it? Seems like such a simple question, yet answering it for Sagittarius A times required 50 years of effort, hundreds of scientists, cutting-edge technology, and international collaboration. Sometimes the most fundamental questions are also the most difficult to answer. As we look up at the night sky, we might wonder about our place in this vast cosmos. Sagittarius A times is completely invisible to our eyes, hidden behind dust clouds and too faint at visible wavelengths to see anyway. Yet it's there, a supermassive black hole at the heart of our galaxy, around which hundreds of billions of stars, including our Sun, perform their slow cosmic dance. We're connected to Sagittarius A times by gravity. Its mass contributes to the gravitational field that shapes our galaxy's structure. The heavy elements in our bodies were forged in stars that orbit that same galactic center. Stars that lived and died and scattered their processed material into space, providing the raw ingredients for new stars, planets, and eventually life. We're made of stardust, as Carl Sagan famously said, and those stars orbit Sagittarius A *. But we're also connected by something more abstract and perhaps more profound, by our desire to understand. A black hole generates no light, thinks no thoughts, cares nothing for our existence. Yet we care about it. We've devoted careers to studying it, built instruments to observe it, developed theories to understand it. This drive to comprehend nature, to figure out how things work and why, is one of our defining characteristics as a species. The image of Sagittarius A times that bright ring surrounding the dark shadow is an image of the ultimate unknown. The interior of a black hole is hidden from us, not just by distance or technical limitations, but by the laws of physics themselves. No signal from inside the event horizon can reach us, ever. In a universe we're slowly but steadily coming to understand, black holes represent an irreducible limit to our knowledge. Yet even this limit teaches us something. It shows that nature has boundaries we cannot cross, secrets she will never reveal. This humility, recognizing the limits of knowledge while still striving to push those limits as far as possible, is an essential part of the scientific worldview. As we close this journey, consider that everything we've discussed, the physics, the observations, the theories, the technologies, represents humanity's current understanding. In 50 years, or 100 years, or 1,000 years, our knowledge will have advanced. Future generations will look back on our EHT observations, the way we look back on Jansky's first detection of radio waves from the galactic center, as an important first step, but crude compared to what came later. Perhaps they'll have movies of Sagittarius A times, showing the dynamics of the accretion flow in real time. Perhaps they'll have measured the black hole's spin with exquisite precision. Perhaps they'll have observed the merger of Sagittarius A times with Andromeda's black hole and detected the resulting gravitational waves. Perhaps they'll have developed a complete theory of quantum gravity and know what lies at the singularity. Or perhaps they'll have discovered something we can't even imagine, answering questions we don't yet know to ask. That's the exciting thing about science. It's an endless frontier. Each answer creates new questions. Each observation reveals new mysteries. We'll never run out of things to discover, phenomena to explain, puzzles to solve. Sagittarius A times has yielded many of its secrets, but it will keep us busy for generations to come. And beyond it lie countless other mysteries waiting to be explored. So when you look up at the night sky on a clear night, spare a thought for Sagittarius A times the massive, invisible presence at the heart of our galaxy. Think about the brilliant ring of plasma orbiting at nearly the speed of light, the warping of space-time that creates that distinctive shadow, the event horizon beyond which no information returns. Think about the scientists who've devoted their lives to understanding it, the technologies developed to image it, the theories tested against its observed properties, and think about what it represents. The universe's most extreme environments, where space and time behave in ways that defy intuition, where gravity becomes so strong that not even light can escape, where the laws of physics are tested to their limits and sometimes beyond, where the known universe ends and the unknowable begins. We've finally measured how big Sagittarius A times is, and in doing so, we've taken another step in humanity's long journey to understand the cosmos and our place within it. Conclusion: the wonder continues. The measurement of Sagittarius A** size marks a milestone in astronomy, but it's not an ending, it's a beginning. Each new observation raises questions that demand new observations to answer. Each theoretical prediction requires testing. Each technological advance opens new possibilities. The black hole at the center of our galaxy will continue to be studied for decades and centuries to come. Its secrets will gradually be revealed, yet it will always retain an air of mystery, a reminder that the universe contains places we can observe but never visit, phenomena we can measure but perhaps never fully understand. But that's what makes science exciting. That's what drives us to build bigger telescopes, develop more sophisticated theories, and push the boundaries of our understanding ever further. The quest to understand Sagittarius A times is part of humanity's larger quest to understand the universe, where it came from, how it works, what our place is within it. We've come a long way from Jansky's mysterious radio hiss in the 1930 seconds. We've imaged a black hole, measured its size, tested Einstein's equations in the strongest gravitational field accessible to observation. But the journey continues. The next generation of observers will see things we can barely imagine. They'll answer questions we're just beginning to ask, and they'll discover new mysteries to perplex and inspire future generations. This is the legacy of Sagittarius A**, not just what we've learned about one particular black hole, but what that black hole has taught us about doing science, about the universe, and about ourselves. In measuring how big it is, we've measured how far we've come and caught a glimpse of how much further we can go. Thank you for joining us on this journey to the heart of our galaxy. If you enjoyed this deep dive into Sagittarius A times and the supermassive black hole at the center of the Milky Way, please like this video and subscribe to our channel for more explorations of the cosmos. Clear skies, and keep looking up.